Participant, good afternoon, everyone. Good evening from Sydney. And yeah, I'm Rohit. So yeah, we got two sessions. Today, the session number 3, what we're going to discuss is about bridge principles. I just want to bear with me. Please bear with me, because if you notice any spelling mistakes or grammatical errors in this presentation slides or anything, and please correct yourself. So this is a short bio about me, and this is the disclaimer, and then as my thought about it, and then this is the presentation format. We already discussed we had already 2 sessions. We discussed about the introductory session and the bridge element performance. We discussed in our last session. Today we're going to discuss about bridge principles. So I'm going to give you a brief overview about what we're going to discuss today. I will just brief about what we discussed so far in the first 2 sessions. Then I will give you a overview about bridge design philosophies, the way the course develop. And I spent a bit of a time about waterway and flood design. That is quite important. And touch base with geometric designs. The barrier designs, I think the concepts we discussed in our session 2, there was assignment as well. And then I will jump onto collision protection. This is quite important in the bridge design. Then we'll touch base with the miscellaneous structures, and then the road sign and lighting structures, the fire requirement in bridges, not all bridges, some bridges. And we're going to discuss in the session 14. Then I will spend some time with the fatigue design, because the bridges are subjected to fluctuating loading all the time. The fatigue design is very important. And I'm going to discuss with the common material used in the bridge construction, that concrete, reinforcement, and steel. Then I will give a very brief introduction to bridge loads. This put the foundation to the next session. And during the last session, I gave you a question regarding the barriers. Some of you already sent me the answers. I will respond to you all during the weekend. And because with the session 3, actually the bridge design part 1, we're going to complete. So you will realize what I mean by bridge design part 1. So overall understanding about what is bridge, how it's going to perform, what we need to do when we are going to design. That's you can have a clear picture about now after you finish this session from 1 to 3. And then the next week I'm going to give you a break, and I will take a break myself. But instead you're going to get a set of questions regarding session 1 to 3, and then to refresh your memories and for you to understand what certain element we discussed before and how you going to apply them when you are going to design a bridge. So I will send you that questions over the weekend with these slides. And with this presentation submission, I think the presentation, the last time there were a couple of questions during the Q&A session. I think I sent the answers to that one. I share with all of you. I think now Chatumi had already organized the place you can find the previous sessions slides and all the resource material. So please go there and download and then read through. And then if you need more information, please let me know. Then I will start the presentation. The session 1 and 2, if I just put in a few lines, what we discussed in the session 1, we discussed when you are a bridge designer, the people you need to get involved with, and the quality assurance and quality control. So you need to look at during design and construction. The session number 2, what I discuss about the bridge behavior. This one, I try to get 2 extreme end in the bridge design. One is the very standard form of I-gird bridges against the kind of a very rare kind of a bridges people has to build a balanced cantilever bridge. Then again, I went on. I explained to you between the construction techniques and the construction technique in both bridges and the both ends, and the cost differential involved, etc. And then we talk about one of the most not people that serious about, but one of the most important element in the bridge is a bridge barrier. I think we discuss in detail the risk assessment you need to carry out. The one reason I explain it to you at that bridge barrier design risk assessment, if you are a bridge designer, you need to look at you are facing a lot of risk when you are designing a bridge, and those risks you have to eliminate one by one. That is what you're going to do when you design the bridge. Anyway, we engineers we basically take a lot of risk, and we use scientific principle to resolve them. That is our job, and that's what we are doing. And then I gave you an example about the link slab bridge, and then the way how we're going to determine the limitations of when we were selecting certain elements in the bridge. For example, we looked at the example with the link slab 150 meter against 300 meters. People can come up with answers, you can come up with solution, you can design those bridges, but then when you try to push the boundaries, then there are limitations in there, but you have to overcome a lot of other issues when you want to pursue with that design. So these are the important thing when you design a bridge. You need to look at. Then I just touch base with the bridge articulation and things, and that is what we discussed in the session 2. Then today we're going to discuss about the bridge design philosophy. So the bridge design philosophy based on what? That is what this particular slide shows. So the simple example is you can design a bridge, right? It won't collapse, it serves the purpose, but you can see in here, you didn't design your bridge with enough clearance in there, right? There is a time, there is a possibility. It's already, you can see from this picture, this truck is pushing the bridge. So there is a board in here, low clearance. I think it should have been a couple of meters before this bridge to 3-4 times to tell the driver there is a bridge with low clearance. You have to take precautions, otherwise you have to design precautions. If you look at this picture at the top right-hand corner with earthquake, you design a bridge. That bridge you design for your traffic load, that is what we designed for bridge, but you haven't considered the earthquake loading. Sometimes this loading might not be, you can't predict properly. So you can't predict this one in a proper way. The earthquake you can't predict. This is what's going to happen. But you can design that one, you can detail that one to resist that one. For example, it can crack, not collapse. Because if it is a bridge is collapse, it's not like something crack or in your house. So you just go there and put a bit of a scaffolding and jack that one and fix it. if a bridge is collapsed, it's collapsed. So you have to destroy that. You have to rebuild a new one. There is no way you jack this bridge up and then put a stitch bow and refix it. You can't do that one. And you can see this, the other picture I am having here, failure during construction. So you design the bridge, everything is good. So you, during the, yeah, this is a pedestrian bridge. It's a very famous one. I think it's, you read about this one. It was in the news maybe a year ago also, or last year. I think the, or before, I'm sorry, I forgot the exact date, but you design this bridge for people to walk after you finish everything, but yeah, you missed the during construction. It's going to work or not, right? So you think it's someone else's responsibility. Because of that, it's okay. And yeah, it's a contractor's responsibility. It's not me. You can push the responsibility to someone else. And yeah, because when you are designing a bridge, it should be functional, it should serve the purpose. In addition to that, it should be able to build. The one, this picture in the middle is the failure due to wind. I think this is one of the quite famous pictures. I think every structural engineer should have seen this one before. This is the Tacoma Bridge, the bridge failure. I think if you are the old engineers from University of Peradeniya should have seen this one. I think Professor Mahalingam should have played this video. I watched this one when I was a master's student, when I was studying structural dynamics. Actually, that video my professor in AIT got from Professor Mahalingam. I just want to touch base with you. The wind engineering in the bridge wind dynamics is quite important. After this bridge failure, I think around the world, everyone started doing research and try to understand the fundamentals of the behavior of structures due to wind. This is the one of the area, at least read some articles and get some appreciation and get some understanding. And the other picture you can see I put in here, accident during construction. Yeah, it could happen all the time when you are doing a bridge construction, the major construction. This is one of the segmental box girder bridge. While they were building it, there is some issues with the gantry, and then this the box girder didn't collapse, but it's to its, you can see there was a separation in here. So it's a lot of work. They had to they unload this segments again, and then the has to do so many work. And the other thing, like the one in the picture at the right in the center, the bottom center, the failure due to flood. I think you saw this picture last time. The last session, I have the same picture. You design, everything is good, but you can see you haven't considered that this bridge you just put on an abutment just sitting on a soil, and then during the flood, the abutment washed away, the whole bridge collapsed. So you can't cut this one into half and build the other half and say this bridge is going to work. So you can't do that one. So this is a very small thing. You can see the amount of money you're going to spend to design and build this bridge. And if you just ignore this little thing during the course of the design life, is 100 years plus. I think there is a possibility this bridge is going to collapse. And the other one in the bottom right hand corner, this is one of the famous incident as well as the ship collision. You can see there's a ship collision, the bridge has the one span already gone, right? One span already gone, and then you can't use this bridge anymore. You had to rebuild this one again, the ship collision. So when you are designing a bridge in a waterway, you have to consider that one. I have this picture underneath on the left, bottom left-hand corner, alternate load path. This is the bridge. You're going to see this picture again, a design to like, for example, if I give, if a vehicle impact on this bridge, it's not going to collapse. It's the way this design. It's a similar way you can see on the top, this so, excuse me, in the top middle, the picture that protected from collision. You can see this is a bridge go above the road. There are barriers is protecting these three small circular columns. So the designer might consider that if this one hit, if there is an accident, so they want to protect that one. Sometimes the designers can design this one to even the one column can crack, but a steel bridge won't collapse. They can go back and fix it. So we're going to learn this thing today. So the design philosophy of the bridge design is developed based on these incidents. So when you are designing a bridge, wherever it's according to the location of the bridge, you can't have any of these incident happening. There are so many other things I haven't put in this slide. We're going to look after. That's why when you are designing a bridge, there are so many volumes of design codes. For example, in Australia, we have 9 design volumes to design bridges, not bridge, to design bridges. There are many type of bridges. There are so many books, so many design manuals available for you to review and design. So when you are designing a bridge, all these elements you need to consider. So then there is a way to a systematic approach we need to have to address this thing. So that is what we're going to learn. That is what you're going to you can see, you can find in design standard. So what is design philosophies? What we're going to consider? The bridge shall be designed. Design shall consider intended function. Mainly bridges we design for to support traffic and or to move the people, move things around or connect point A to B. And it should be aesthetically pleasing. It should be constructible. It should be maintainable. I think I went through this one in the session 1. It should address the sustainability, climate, and safety in design. I think we discussed this element in the design 1. I think if you design a bridge 25 years ago, the sustainability word is not there now. I think it's there, the climate change. 25 years ago, when I was start designing bridges, understand if they start working as a structural engineer, these words were not there. But now bridge design or any design, sustainability and climate change, you need to consider. The bridge design shall be based on engineering principle. Definitely, what we learn in our university from 4 years we spend in the university and more years we spend in the design offices. We learn those engineering principles from the uni, and then after that read in the books, and with sharing the knowledge with practicing engineer. All these designs are based on engineering principle, based on the mechanics, based on the analysis, and this based on the experimental data and experience. A good example in the experimental data, you know, when you're designing a reinforced concrete section in different design codes, you're going to see the different the model we use to represent the behavior of the concrete element and the reinforcement. So these are based on the experimental data, and the sum of the bridges when we design is based on the experience. What you can see in the background of my background of me, that's based on the most of the engineers' experience. And if you design a cable stay bridge, the design is mostly based on the engineer's experience with the design codes. And the structures shall be designed and detailed fall in ductile manner after they reach the ULS design ultimate limit state design state. You know, the bridges collapse due to fatigue failure. They are not ductile. So you need to make sure that you can see the bridge is cracked. The structural engineers will understand this bridge is having a problem. What is the extent of that problem? How serious is that? so we can make a decision. So you need to make sure that your design fail in that one. I think I put an example to explain this one. You will see at the later part of the presentation. You need to design with them with the alternate load path. So like for example, if there's a collision in there, if you design that one to make sure that it's not going to collapse in a straight away, yeah, the bridge can crack, and then there may be a significant damage to the bridge pier, for example, but it still won't collapse. You can go and fix it, and after that you can use it. And the segmentation of the structure to limit the consequence of any failure, rather than bridges coming down as a one unit, you can make sure that it will it's a segment of the bridge is fail. Like for example, it will crack, and then the piece of the concrete maybe fall down, or the whole bridge girder, the system will come, because this is come where when you are detailing the bridge, you can see that one. For example, I think the couple of times when I explained it to you, there was a lateral restraint block we put on a bridge. Another thing, when we were going in detail later on the bridge design, you can see we put earthquake buffers in the bridges at the end to make sure that that sort of thing won't happen in the bridges. And the material and properties, the degree of ductility. So we're not going to use uh, the material with less ductile material. For example, when we were selecting the reinforcement, we have to look at what sort of ductility range of that materials. And when we combine, for example, you're going to learn it later in the presentation today, the concrete, the steel, and the strands together, how these these three is going to perform, and then how you're going to maintain the ductile behavior of the bridge. And the mode of failure is very important. I think you saw in this one, for example, the earthquake one, and this the construction one, and this the wind, and this flood. I think you need to look at the mode of failure. For example, that bridge they designed, the flood one, they designed everything is good, but they didn't properly look after the abutment design. So the safety and performance of structures is very important to make sure that you design the bridge to perform the intended function, what we discussed at the beginning, the quality control, the supervision, and the unavoidable imperfection when you are building a bridge. I think that if you are building a bridge, it's not that easy for you to construct the bridge deck, because we are using the concrete, pre-stressed concrete element. They are not short length, they are 25 meters, some in 100-meter length. So these elements have a significant deformation pattern. I think they are very difficult to predict. And then the experience and skill. When you are a bridge designer, the bridge design experience and skill is very, very important. Then the documentation and design assumption. I think we discussed this one in our first session. Why the design documentation and design assumption, you need to make sure it's in there, because you design a bridge and 2030, it's going to last more than 100 years. Then 10, 15 years time, you won't be in that design office, so you won't be there. But the road authorities, they have to maintain this one. If they come across a problem in the future, then they need to know your intent of the design. That's where you have to document this one. If someone say everything is in the design drawing, that is not right, because you have to write down your assumption. If someone say, oh, the assumption is in the bridge design code, so then I designed this one, chartered engineer signed that one, drawing is there, that's the end of the story. That is not right. So you are liable with this one, because you need to make sure that the future generation can understand what you have done today. You need to have a proper design documentation to ensure that your design intent is documented. The design philosophy is not based on the piece of calculation. You can say that's and just interpreting code the way you like, copying a one equation from one place to an Excel sheet or a piece of paper is not the design. It's much bigger than that. It's a larger picture you need to look at. If you just do a calculation and do something, your bridge will end up one of these conditions during the 100-year design life. So please take this one seriously. That is what a lot of research, a lot of people spend so much of time, put them in the documents. I think it's better read and appreciate what is in there. That is very important, because it's the collapsing a bridge. It's cost a lot of people life, and it's make a significant damage, because you can't just build a bridge within overnight. Then design life. I think I'm not going to discuss this one in detail again, because we discussed this one in our first session. So I think the bridge design, at least we designed for 100-year design life. When I looked at the British standard, I think British standard mentioned that when your intended design life of the bridge is 120 years. So the other one, we designed bridges to satisfy limit state. I think the one is the ultimate limit state. The other one is a serviceability limit state, where we make sure that the design is satisfy the both limit state criteria. So the ultimate limit state criteria, we make sure that the during the design life of the bridge, there is a 5% probability of accident during the design life. Whatever the loads or load combination you're going to assume in your bridge design, it's not going to exceed, there's only 5% chance will exceed that one in 100-year design life. So another thing, we designed the bridge with average return interval of 200 years, because when we design a bridges, for example, when we were designing ultimate limit state, you always used to multiply your loads by another load factor to take into account the uncertainties. But why we average return interval is 200 years. That's we define, for example, wind, earthquake, flood. Those loads you can't quantify, but we quantify in terms of their return period. The flood, you always see this, you experience the flood level, the different times. Sometimes the recent flood events, you get really big flood events. So we define with the return period, and we had to design the structures with the stability, strength, failure or deformation, deterioration, and the strength and brittle fracture. So the strength is quite obvious. We provide enough reinforcement and we select right concrete, and we looked at the failure or deformation. We control the deflection, and we look at the deformation. For example, the bridge always got the time dependent deformation creep sink rate. I think the deterioration of the strength and the bridge, we look after that one in the durability. We select the right material, we employ them, we build them in the right way, and we make sure that the bridge is not going to collapse, because we make sure the bridge will fail in a ductile manner, not like a brittle fracture manner like in fatigue. So the SLS design, we got the same principle, the 5% probability of accident per or average return interval of 20 years for your flood or wind, and the deformation, like example, bridges are sitting on pile foundation, big foundation. We make sure the deformation of foundation, permanent damage due to fatigue, cracking, corrosion, vibration, flood damage, all those things we cover. For example, you can design a bridge with beams and everything, but when people are driving on there, people start complaining, bridge is vibrating. It's very difficult for us to stay on a traffic. So there are a lot of situations. I think reported. I think the one good example is the Millennium Bridge in London. I think when they just opened, I think you saw this one, that video, and the people, when they start walking along that bridge, it looks like they said like having a couple of beers within the bridge, because when they were coming to the other end, they were so dizzy. Yeah, and so the SLS, the serviceability limit state design, is one of the important thing. It is not the design, you just make sure that you check the the deflection limit satisfied, is everything is good, because you have to put you have to think beyond the boundaries when you are designing a bridge, because you have to think and spend the time and look at your drawing, and when you detail it, there is a possibility here and there. If you think like that, better to list down that one, make sure that you cover all the bases. Yeah. uh, it's not like, or else you can have your own checklist, and then you can take them on, and then you can develop yourself, you can discuss with someone else and get his opinion, and then develop that one to make sure that you design the right bridge. Another thing, that is what I said all the time, if you send your design to the reviewers, I think you will get a better outcome, because if you get a third person opinion, the if you miss something, there's a possibility that they can find out that one. And when the bridge design, we have to use the analysis methods are very important. We normally use the linear elastic methods, and you can use the nonlinear analysis. The nonlinear analysis, and then the time dependent analysis. These both interrelated, and normally when you design a bridge, it's time dependent, the creep shrinkage you can take into account. You can incorporate this one into bridge model. So when you model the bridge in 3-dimensional modeling, so your pile foundation is in the soil, then you have to get the soil interaction. You can incorporate that one into the model. For example, all those elements, when you combine them, you have to perform nonlinear analysis, especially if you analyze your bridges for the earthquake and the dynamic analysis. You have to perform nonlinear analysis. You can see when we are proceeding with the next session how we're going to employ them in our analysis. And the design actions you need to take into account, of course, the external forces like a traffic load, wind load, and those things. But the indirect, the external forces is the direct action or versus the indirect action. The indirect action is like if you get the deformation. For a good example is the creep shrinkage and the construction, the post tension, the pre-stress. When you have all these elements that create the deformation in your bridge, you need to consider them when you are analyzing and designing it. And the definitely the design capacity, the under strength. So you need to make sure that you calculate your design capacity and the strength of your structure based on the proper design standard. For example, you can't use the BS 8110 to design. You have to use BS 5400 standard. So need to make sure that one, same as in Australia, you had to use AS 5100 series to design bridges, not AS 3600. So that design codes they develop to design two different structures to make sure their performances met. And you have to verify your design. Of course, when you design, your ULS capacity has to be bigger than any design actions due to the design effects in there. Because when you put the traffic load on the bridge and your dead load and superimposed dead load, wind load, earthquake, all sort of load, when you combine them together, whatever action you calculated, your design strength, you have to make sure that it's higher. So you can't say it's good for traffic, but it's not good for the wind and earthquake. You can't design a bridge, so you can't design any structural element. And then the serviceability limit state side, you need to make sure your deflection, cracking, vibration, you looked after, like a deflection and vibration more or less combined in the bridge design. For example, when you design the buildings here, but you're going to your deflection limits, you make sure like L over 300, but when you design a bridge, your deflection limits go as large as LO 800 to LO 1000 to make sure this deflection and vibration, because most of the bridge design we are not doing vibration analysis. My experience is it's very difficult to predict that one. Even if you predict, it's not going to make that way. You have to test the bridge. So then you have to rectify that one after you build the bridge. That's very difficult. Yeah. And the verification by calculation and testing and combine. For example, you perform calculation, you design your bridge, you get your dimensions of your concrete girder, and then your reinforcement content percentage, the pre-stress percentage, you detail everything, and it's based on your calculation. But when you say 40 MPa concrete, the cylinder strength 40 MPa is equivalent to closely equivalent to 50 MPa cube strength. So you have to make sure that they achieve that one. How are you going to do that? You have to test that one while you are constructing it, or else sometimes we design bridges combining both together. But this is like this one is not separate from the construction, and design is going together. So you have to verify them. And then the design need to consider accidental forces like we looked at before: wind, earthquake, flood, and the impact and collision. I think these are the things you can't quantify how much is it. Yeah, but you can quantify live load model. You can test, even if you have to control, you can put because you can see there are some bridges, there are height limits, some bridges there are weight limits. You can impose that one, but for the wind, earthquake, flood, and impact collision, you can't quantify that one, how much it is. Very hard to do that one, and you have to consider them. And then you have to design your bridge with appropriate redundancy, protection, robustness, and avoid collapse. This is one of the important thing when you design the bridge, to make sure that yeah, it can sustain, it can absorb this load, it can support this load. But if it is overload, but still it will crack, it will show the deformations, but it's not going to come down. So you need to make sure that you design your bridges to match with that one. Because I'm not going to explain this one in detail. If you are interested, you can read through textbooks. Each and every one of these elements is explained in chapters. And you have to consider, when you design and constructing a bridge, you are looking after the environmental impact, especially when you are building bridges across the rivers, and then while you are building it, while you are servicing it. For example, sometimes I can give you one classic example. You can build a bridge across the river. The people might argue, because the bridge will get rainwater, and the river always get all the dirty water everywhere. Because of that, I will collect the water and let the downpipe go straight down to the river, because it's okay. What happened if on top of the bridge there is an accident? Let's say the tank accident and spill a lot of oil on the bridge. When you have your bridge with the downpipe straight down to the river, you can see you're going to pollute your river. So there are so many things you need to look at when you're detailing. You can say it's not going to happen, but it could happen, because we are designing these structures for more than 100 years. Another thing, the flora, fauna you need to protect, and these are the things you need to consider. I just list only few, you can have many. And then we discuss about the safety in design you need to consider when you're designing a bridge. I think this is quite important, because you can't let the people to get injured while they are building it or while they are maintaining it. You can't eliminate all the risk, but at least you can do your best. And while the contractors, when they were building it, they need to look after their part, while the road agency is maintaining them, they have to look after their part. So this is the collective effort. But what you need to make sure that you do your part as a designer. And the sustainability is one of the important things when you design a bit. Whole of life cost is very important. We're going to discuss this one one of the late session, I think I explained this one in the session one as well. Bridge design is not coming up with the cheapest solution. Yeah, no, everywhere you go to the today world, everything they think is good is cheap. No, not that. When you design a bridge, it's going to last 100 years. And then you need to make sure that you look after, you build your bridge to last 100 years. You minimize the maintenance. But sometimes you have to put more money at the upfront. You have to make sure you look after all the quality control. You can have a designers come up with the really quality bridge design. Everything is in there. But if you build that one in a very bad way, it's no point having that one. Let's say you design right, you build right, but if you don't maintain it, for example, I explained last time, the session 2 and the bridge bearing, like a design life is 35 years. Someone say we don't have money to replace that one, let it be for, it looks like okay to me, we'll leave it for another 15, 20 years. In the one time, the bridge might slip and then the one bearing fail and everything fails. So then your whole bridge might in a position you can't repair it again. Because of that, this everyone's responsibility. And the durability, the life cycle assessment, you need to make sure, even I think in the future, like in the 100 years time, this bridge, if you build today, the 100 years time, we had to dismantle and dispose that bridge. You need to pay attention to this one while you are designing. This is not common for bridge. Any structural engineers, any engineer, not the structural engineer, any engineer has to keep this one in the mind when they were designing it. It doesn't matter electrical or electronic or civil or mechanical or whatever discipline. And the heritage and the water, air quality, I think noise, biodiversity, these are the things you need to preserve. You can't build a bridge destroying a heritage that is important for the future generation. You can't destroy the water that is a precious thing around the world now. You can't destroy the air quality. Now, I think time to time, everyone is experienced the air quality. You can't build the thing is noisy, because when you are building a bridge, the traffic is, you are increasing the traffic there, but you need to understand that there are people living nearby. You can't disturb their livelihood. You need to make sure you look after that one. When you are building a highway infrastructure or bridge, you can't go back and cut the precious, destroy our the biodiversity. For example, sometimes we have some species, some forest we preserve for the future generation. You can't go back and destroy them because you want to build a cheap bridge. And a cheap alignment, you can have it, you can reduce the cost by 10%. That doesn't make any values. It doesn't satisfy the actual objective of this design. And you have to use the right manufacturing technologies, material and installations and disposal. Those things you need to consider. And the resilience to adaptability of asset in respect of climate change. I think this is the one good example, this climate change. The people do flood modeling and think they predict it's not going to go underwater even a 1 in 100-year flood, but in this flood, the bridge is underwater. Then everyone is asking the question, how do you calculate 1 in 100-year flood? But you can't blame them, because sometimes when you are modeling those things, the data you're going to use is the old data. If the data you're going to use in your model is not accurate, you can't predict that one. You can say the other one, what is happened to bridge. This is the bridge in the river. The durability thing, you can say this is falling and all this reinforcement corroded because of the chloride and the contamination. So because of that, the durability is one of the very important thing. And the middle picture, you can see that the safety in design, I think they are building a really big bridge, but they didn't pay right attention while they were safety protocol and attention. You can see this crane is almost collapsed. Then this is the when you are designing a bridge, that is the philosophy you just need to have in your mind. This is not just to a design calculation, just go and copy a design code across to your piece of paper, and then you say, I did the design, is good. Not that. Yeah, you have to look at so many other aspects when you're designing. Not only you design, you have to look at how is going to build, and then how is going to maintain, how it's going to perform, and all those things you need to keep in your mind. I think you need to make sure that every the tick box is every one is you ticked at the end of the design. I think especially the road authorities has to develop their own checklist to make sure that designers and contractors are uh, address this thing. What, yeah, your intent has been achieved or not, because that is very important. Any question in here? Any question?
So I have a question.
Yeah, Diane.
Yeah. How often you design for impacts or collisions in a bridge? Generally, like for each and every bridge, or you select several bridges depending on the importance level?
Um, uh, yeah, I think that's a good question. So we designed the bridge for collision load irrespective of the number of occurrences. I'm going to discuss this one latter part of the presentation. So then after that, if you still need any clarification, please come back to me. I will explain it to you.
Yes.
Thank you
You.
very much for asking that one. Any more questions? All right, then I just jump into waterway and flood design. I think we discussed this one in detail. When we were designing the waterway and flood design is very important, because even if you in a highway, for example, now we are building a very long highways, all countries, everywhere. We are building highways, and sometimes the bridges are like serve the people to cross some point, but sometimes bridges serve like a culvert, for example, cross drainage facility. Yeah, bridges we design, we call them floodplain bridges. Yeah, we let the water to go under the bridge. Yeah, and when you are designing a bridge, you have to make sure that you make your bridge is flood immune. So normally the standard practice is it's all depend on the road authorities, and it's depend on from country to country. You make sure that the bridges you put about 1 in 100-year flood level is depend on it's a motorway or it's a highway, it's a local road. Depend on that one, you can set your immunity level. But when you are designing a bridge, you need to make sure that your return period 1 in a 2,000 year, like you saw that the first slide, the abutment collapsed because of the flood. So you need to make sure that you address that one. And the hydraulic capacity of the bridge is not going to catastrophic failure like you saw there. These are the things when you design the bridge. You need to make sure that your bridge stop it in a right level, and you put the right forces, right hydraulic forces into the system, and you make sure that your bridge, not only the bridge and other element like abutment and the fill and everything, batters and everything you design, if it is support the bridge to support this environment, these forces, these flood forces. I gave you a lot of information in this one. I think you can use this one as a reference, but these numbers may be different from code design standard to design at standard, and from the road authorities, they might specify their own numbers. And you can see, you have seen this picture before as well. We put this is a bridge building across a creek. So 1 in 100 year flood level. So we have a freeboard, our soffit of the bridge, we put half a meter above that one. And this bridge, but in 1 in 2,000 year flood, this bridge is underwater. That is one of the ultimate limit state event. Bridge is underwater. So, but we need to make sure that it can go underwater, but it's not going to collapse. Yeah. Because you can't design a bridge to make sure that it's immune for 1 in 2,000 year flood is going to be really a difficult task, and it's very costly. But you need to make sure that 1 in 2,000 year event is very rare. You need to make sure that your bridge can go underwater, but still make sure that it's not going to collapse. It's not going to wash away. And these are the pictures, what happened with the flood. I think you saw this on the abutment collapse, and you can see this bridge. You can see there is no way you can stop all these debris, and then this the debris, sometimes the log impacts and those things. You can see what happened to this bridge pier, and the bridge already twist and it's not in a serviceable condition. So therefore, when you design a bridge, especially in a waterway, you need to make sure that you design the bridge for debris, hydrodynamic forces due to debris mat, and the log impact, and the shipping impact as well. So we're going to look at this one later. And the piers and abutment avoid trapping. You can try to get your detailing right and try to protect them. You can't do 100% that one as much as possible. And then the remain stable, because if there's a massive flood flows, I think the main problem in the bridges, there's a cover, a lot of the material, silty material will washed away, and because of that cover, the bridge, the pier length will be increased, and because of the flood force, and there will be a situation that bridge will be unstable. You need to make sure that you capture that one in your design. So when you design when you are designing bridges, I put this. These are some of the design data you need when you are designing a bridge, because we designing the bridge for 100 year and 2,000 year ARI. So to calculate what is the forces, you need to know velocity, and because of the flood, you can have a cover in your bridge pier. You should know what it is. And again, you need to make sure that what is the flood level, to make sure that your soffit is you place above the flood levels. And you need to know what is in the ultimate limit state, the flood level, to see whether the bridge is underwater or not. If it is underwater, you need to provide, if required, the restraint, the vertical restraint, to prevent the bridge's uplifting. Because if the bridge is uplift, then the horizontal force due to the water, it will push away, then your bridge will displace, and then you need to make sure it won't happen. I think that's why in the bridges, we provide the lateral restraint block as well, to make sure the bridge will deform but is still not pushed away. And these informations are very important. This design data is required when you are designing a bridge for flood. Any question about this one? All right, then. When you are designing the bridge,
Rohita,
yes?
I have a question. Sorry, I got late. Windsor Road Bridge. Windsor Road Bridge. You know where it is. We just rehabilitated that one, and last flood, but 1 year back, it went underwater. I asked the engineer at the time, what was the return period. She told me it was 20-year return period. Okay, so argument was RMS knew that it's going to go underwater, and they purposely selected this 20-year because all the approach roads going to go underwater in any case. So there is no point, absolutely no point, designing a bridge more than the flood level at the road, because all the roads will be flooded. So no point we are having a bridge above the flood level, right? So that was the answer given to me, right? So So similarly, when I was in Sri Lanka, I knew that Colombo, that spillway, there is a bridge over that spill tail canal. That bridge always, when there is a flood, it gets washed off, and then people told me at that time they knew that it's going to be underwater. So that's how the design was. So your position is, if we laterally restrain the bridge, I think which is the case in Windsor Bridge, is that's okay, isn't it? We don't have to design anything for 100 years all the time.
No, we had to design I think we had to design the bridge for 1 in 100 year, the SLS and the SLS 1 in 100 year and the ULS 1 in 2000 year return period. We had to design for this dynamic forces and the cover everything. We need to design for. But for example, if I give you everywhere in the world, if you get a flood 1 in 2000 year event, your approach roads will be washed away. The difference is this one. Like I have this saying all the time. If you have a pothole in a road, while you are driving, people never drive through the pothole. They will slow down and they will avoid the pothole, unless otherwise you are really stupid enough to drive. But if there is a crack on a bridge, you can see that one is on a newspaper. We structural engineers, we know it's not going to collapse, so nothing wrong with that, but it's in a newspaper. That is the perception of the public, and it's around the world is the same. So the argument in here is the people say you can't access the bridge. Why should I design? That is not right, because your access road you can reinstate within a week or two, or less than a month. But if your bridge washed away, the cost, you have to remove the bridge and rebuild that one. It's a significant cost and time. You have to close that whole highway for that period of time. Because of that, you have to design your bridge to make sure that it can carry all these the heavy flood loads and the monster flood events. It can resist. It's serviceable. It's serviceable.
Okay.
And yes.
Yeah. So what you're saying is, if you design for those loads, even it goes underwater, it will be okay. And is that how
of course
you feel?
Yeah.
Okay. All right. Yeah. Thanks for that. Yeah.
Thank
All
you.
right.
Thanks for sharing this experience with the others.
Because I was puzzled by the answer. Like, this bridge was built only 1 year ago, and next rain it went underwater. So I was asking them, what happened?
That is, to
and
me,
we never had we never had 100-year flood in Sydney. Okay, we had only 20 years or something.
Yeah, but the like with the climate change, nobody knows, right?
All right. Okay. Thank you.
Thank you.
Continue. Okay. Bye.
The another thing, and the geometric design is very important, because without geometric design, you can't get your bridge dimensions. I think we discussed this one in the session one. I'm not going to spend so much of time in here. The one thing I will, I want to emphasize you, like you design your bridge, so this picture in the middle, without enough clearance, vertical clearance, you could see that accident happen, right? So then this bridge is not going to be serviceable. Therefore, you need to make sure that your bridge have a minimum vertical clearance if you are building that one above a road. So there are minimum requirements. This is depend on from a road agency to road agency, the country to country, different standards. They give you different numbers. You don't want to follow exactly this 5.4 minimum clearance over the road, and for the sign structures 5.4 to 6 makes sense, because the sign structures, part of that sign structure is within the road, then the people are driving underneath. Another thing, I want to make sure that sometimes you build highways and bridges close, they are crossing the high voltage lines. You need to make sure that you have a sufficient clearance for different the voltage. in there. Another thing, when you are designing a bridge, you need to have the road width and the carriageway width to match with your geometric design. This is your highway designers will give you. Another thing, your road authorities will inform you the minimum lane width for the highway we need is 3.5. So we need 2-lane highway, and then the width is speed, and then the geometric design, the highway designers will come up with the right dimension. So you need to design to fit the bridge to fit those dimensions in there. So before you start the bridge design, you need to make sure that is the whole idea of this the slide, to make sure that your highway designer is happy with your bridge dimensions, because you can't, without your width and the vertical and horizontal alignment of the bridge, you can't design that one. You need to make sure that your highway designer is happy what you're going to design also. Both of you has to work together with some understanding. Yeah, because otherwise what happened, if it is changed later on, you have to go back and redo your models, and you will see later on it's a lot of work. And then the next slide, next section, I'm going to talk about the collision. And let's say, Diane, maybe I'm going to explain it to you. Sometimes you will find the answers to your question. Before I talk about collisions, why we need collision protection, you can see these pictures. The first one on the top left-hand corner, you can see this truck is hit this bridge pier. You can see the bridge already twist on the top. You can see there's gap. The spear is already already cracked into 2 pieces. It's deflect, it's fade. You can see the one in the top middle one. You can see this bridge pier almost collapsed. You can see this heavy truck is already hit on this one. And the similar one in the middle, you can see the bridge pier is almost separated. These are the like accident in the roads, but in addition to that, you can see you have to build bridges across railway lines. So the railway lines, there is a possibility that the rail can derail and can go hit. So you can see the one on the bottom center, that picture, you can see there's a bridge going above and the railway underneath. There's a abutment in here. We have this white section, the concrete barriers we built. I think this one we protected. So you can see the one on the picture on the top, they have a guardrail, right? And the other picture, one on the middle, you got a guardrail. You can see the one on the right hand side on the middle, you can see you got a concrete barrier, but still this is a rigid barrier, what we call. You can't prevent this truck is with the momentum in the truck, you can't take, it's just go across and then hit this one, right? So imagine you are building a highway, how many thousands of millions of vehicles will be passing this column during the design life of that bridge. Then if there's a single possibility, there's a massive truck or any vehicle go and hit this bridge, and if this form and collapse, if it is collapsed, the people might die. So we have to rebuild this one. You can imagine how much money over the period of this 100 years, if this accident happened, how much money you need to spend to rectify this one. On top of that, you can see this bridge, you can't let the traffic to be on the bridge because it's not serviceable. So therefore, when you design a bridge going across the highway or railway, you have to make sure that the columns located close to the your highway, you have to be protected. Yeah, you have to protect. To do this one, there's a really very lengthy risk assessment procedure. We can do this one. I did once or twice this, but I think you can do risk assessment and you can justify on paper, but in reality, you can see in this picture, it could happen. You can't prevent that. There is no zero probability, sorry, that you can say it's not going to happen. Even there is a 1 in a million chance. If you say 1 in a million chance, if you convert the traffic into 100-year design life, you can see you will get about few hundred trucks could hit this one of these piers. Therefore, you need to make sure that you protect them. Another thing, I just want to make sure this one, you need to remember that if someone drive in here, if he hit this barrier and if a person die, in terms of the liabilities and insurance, sometimes if you go to the court, they will say, my client died because you haven't designed it's hit this. If he hit the barrier, he won't die because he hit this pier. He died because he hit the pier, and he is on fault because he drive in the wrong way. He speed and he fell on the slab and then go and hit. But if you protect this pier, if you protect my vehicle is going, if you protect my vehicle hitting this pier, if you put a crash barrier in front, then this incident won't happen. My client won't die. So you can't find answer to that argument. So it could happen. Please remember that one. It's not just like just say, okay, it could protect. Yeah, you can't do that one. You have to make sure you have to design. This is accidental force. So this force is very difficult to evaluate what number we have to use. So a lot of people do testing, a lot of experiments. I think you all know this one when you talk about the cars. I think some cars, they say, like, for example, the Volvo is the safest car. They do the crash testing and this kind of a thing. Similar to that one, a lot of road agencies, they did their own testing and they come up with certain design solution. So you know the consequences because of the traffic collision, and it could be on a highway, or it could be because of the derailment of a train. So then it could be not directly go and hit the pier because the not enough low clearance. Yeah, this truck will jack up your bridge free of charge. You can see the picture in the middle. So it's hit that point. The bridge is so rigid. It's a massive concrete structure. So this one split into two pieces, and you can see one in the ship impact one. This is one of the quite serious one. So you have to design your the structures for shipping impact. That's a massive load, and then so the consequences are very severe. They're very damaging, and so not only the people's lives, and in addition to that, your life, your service life of the bridge. Sometimes you have to rebuild the whole bridge. It has to be closed for months or years to rectify. Because of that, you need to make sure you design for that. So how are we going to design? To design that one, the design standard come up with certain solution. For example, if it is in the road traffic, they said you design the column to take 270 kilonewton. This is an Australian standard. 270 kilonewton, that is 270 ton. This is more than almost 4 times the legal 2B trucks in Australia. The weight of this equivalent force is the momentum, and the impact force apply 1.2 meters above this pier. One way you can do, you can put some structure to protect that one, or you can design your pier. You will see later on that, right? If it is a rail traffic, this is a very serious thing, because you know the railway, they are not like the momentum in a railway is massive. The most of the time, you can design that one out. The design force is 4,000 kilonewton and 1,500 kilonewton. And the simple solution, you can put a guardrail to make sure that your train is not derailed. It will be contained, it derail, but still it will be within the rail track. So it's not go and hit the train. So let's say there are places you want to go back and rectify. You can design the structures you will see in the next slide, or you can put a guardrail and you can protect that one in terms of the rail environment. But for the road traffic, still, if you notice, there is a risk that this current design is not working, you can still rectify. And I will first explain about the barriers. For example, one on the top left-hand corner, this picture, you can see this really, the length of the column is almost equal to the length of the width of the bridge. This bridge called pier has been designed to absorb that force. Yeah, it's the same, the one on left, top right-hand corner as well. You can see one on the bottom. You have a barriers, you have a concrete structures to deflect the truck. You protect your pier, direct impact from the truck, direct impact with the pier, you protect that one. You have a barriers or concrete structures, rigid element built around to deflect the truck. The truck can go and hit, but before it hit the pier, is going to hit the barrier, and the momentum will be less than, even if it is hit the barrier, the impact is much less. The bridge pier is strong enough to take any residual force in there. Yeah, so this is a very simple way. Even if you build highways without any proper protection, so yeah, you can go back and fix it over the years. It's not a problem to build the barriers in here. Yeah, this is very important, because the money you're going to invest to build this small concrete element around the bridge pier versus the consequences, if accident happen, the damage and you have to fix the bridge is significant. And the other thing, I just want to just give you a simple example about the collision from a ship. It's very difficult to from the, if you go to Waterway, there are you can go to ships like a 4-ton small boats to a not 40,000. This is a very small range for the container ship. There are container ship up to in the future like 200,000 metric ton. That variation of the massive mass is moving, yeah, passing through close to your bridge. To estimate if this one, if a ship is somehow or the other go and impact with your bridge piers or putting, the ASTO LRFD bridge design specification gives you way to estimate that one. I give you one example. If your weight of the boat is 4 ton, it can move faster, the 7.8 meters per second. If it is a hit with your bridge substructure, it will induce the impact load of 1,900 kilonewton. So if it is a bigger size, the 65-ton the vessel, definitely higher the weight of the vessel is moving slower. If it is the 5.2 meters per second, it should be in knots, but I convert that one to meters per second for you to understand it. The impact force is 5,000 kilonewton. But if you talk about a ship with 40,000 ton. This is a container ship. Yeah, it's in the lower range. You could impact close to 120 meganewton force in your bridge. You can't design the bridge substructure to carry that load. We will see how we're going to tackle that problem. Another thing, when you are designing a bridge with the ship clearances, there are the different requirements. If it is small, the boats and things, you have a 8-meter clearance vertical and 35-meter horizontal clearance that dictate the span between your piers. But if you design a bridge to pass the ships, your vertical clearance is 54 meters, but your horizontal clearance may be as long as 200 plus meters. And then if there's a ship or boats passing by close to your bridge substructure, you can come up with the solutions. I think this one you sometimes may notice if you go to a wharf. I think the ship always berth in a wharf. I think there's a massive impact. We design what we call the fenders, the piece of rubber to absorb that force. If your bridge pier is located within a shipping corridor, you can protect your bridge substructures with fenders. They are not that expensive. These rubber structures, you can put them around. Even if a ship hits this one, it's not going to impact your substructure. Please remember, because it's not like a vehicle is running driving 100 kilometers per hour, but bridge pier, the container ships and things is moving. The maximum speed is 20 knots. Yeah. And the other thing, like in the rail environment, another thing, you can see in the rail track here, we provide what we call the deflection beams. We build around the pier to make sure that is protected. Another thing, this is the one on the bottom. This picture you can see, this is the entrance to a tunnel. There's the horizontal beam. We put this one to protect overhead vehicle entering into the tunnel. This one we designed for 1000 kilonewton horizontal force to make sure that none of the overheight vehicles is entering into the tunnel, because you will learn this one later in the tunnel session. Because if an overheight vehicle enter to the tunnel, it's going to damage a lot of jet fans and so many stuff we are putting hanging from the tunnel roof, and you have to close the tunnel for quite a period of time to fix that one, to make sure that nothing will get into this line before you enter into the tunnel. Your overheight vehicle will be obstructed. There's some areas in the roads, even you can build the clearance bars in here to warn the drivers. I think some of the car parks entrance, I think they used to build this low clearance the collision protection beams to make sure that the overheight vehicles like the double cabs and other thing, the overheight ones won't enter into their car parks. Any questions? Is it clear, Dayani, did I explain it to you, your question before?
Yes, thank you very much.
Yep. So then, any question regarding collision protection and why we need?
Rohita, with respect to collision, now how do you all calculate these forces? Is there a standards? It's a bit of an arbitrary incident, no?
And this one actually based on a lot of testing, this 2,700 kilonewton is in the Australian standard. And these are based on the lot of testing. Yeah, the crash testing. Yeah.
Above the ground level or water?
This one, this is for the road traffic, like this picture,
Right,
like
right.
in here, above the ground level. Yeah,
Above the ground.
1 point. Yeah, I think the quite
the
common
ship
in here.
maybe,
Yes.
Ships may be like a drag force, like, no?
The ship is also direct collision from the ships, like for example in this one in here. Yeah, there are incident direct the ship collision with the substructures. Yeah.
Right.
That one we use the this is the like it proportionate to the velocity and the weight of the weight of the vessel. Yeah, that's why higher the vessel weight, the impact load is higher. Like for the container ships, like us, the 40,000 metric ton one is, you get a 120 meganewton impact is massive. Yeah.
On top of that, you all do put another safety factor? Or?
No, the collision load we considered as ultimate limit state condition to make sure that the bridge is not going to collapse. It can absorb the force. For example, these piers in this picture, we designed for collision load and the foundation, because when we have this impact load, the 2000 kilonewton in here, you can see the amount of bending. 2700 kilonewton time 1.2 is close to 3000 kilonewton plus meter overturn on your foundation on the pier. Your substructure need to we need the foundation need to pile need to take design to absorb that load. We in our modeling we put this one as a loading, and we checked if you not provided, if you not design the rigid traffic barriers or deflection wall or protection around the piers. So we had to design that one.
Thank you.
Okay, thank you, Shilama. Yep. So the
Rohit,
I think the
I have a question, Rohit. I not just a comment.
Yeah,
I have seen many times you have traffic accidents in a bridge approach or on top of a guardrail, and or as you said, as you are correctly pointing out, these bridge piers, right?
Yeah.
And also I have seen many times when you park a vehicle even outside the roadway, like even way beyond the shoulder, you're almost certain to get hit by the passing vehicles. It's kind of a driver behavior. Maybe I have seen many times. I just wanted to say that we are doing the correct thing here. During my lifetime, I come across many travel accidents. Maybe the driver behavior, maybe the changing pattern, or maybe the hydrodynamics. I can't understand, but
I think the one thing is the driver behavior as well. I think the many incident we had in this the overheight vehicle go through the tunnel in Sydney, right? So there are so many protection, but still they just keep driving through. Even they won't stop that one. They just try to accelerate within the tunnel. So it's very, very hard to protect that one. But the consequences are significant. But to me, the in general, if you are designing a proper bridge, I think this impact load, when you check, you don't have to do significant changes to your bridge. So only thing you need to come up with the substructure in a right solution, because the sometimes what the people this is I want to emphasize, the bridge design is not coming up with cheapest a structural engineering solution. Looks like it's working that way, but when you go back and check one by one, you see there are a lot of deficiencies in the designs. Yeah, and even adding to that one, when you start construction, that solutions will give higher construction cost. Yeah, that's the when you design. But the when you design a proper structure to make sure that you cover all the bases, you get the right solution. Another thing, like while you build a highway and you let open that one, if you has to go back and rectify those things, it's not that easy. Because you had to work around an environment, people driving either direction at least 80, 90 kilometers per hour. So you had to work around that environment, not that easy, because we are working on the concrete and reinforcement. They are not easy fix, right? So the construction take longer period of time to build. At least you need to stay 28 days to get your concrete strength. Yeah.
Yeah.
This pollution protection, Rohit, like what is the design philosophy to protect the passenger or the bridge?
I think that's the right question, but these are rigid barriers. I think this is mostly to protect the substructure. Yeah. Yeah, because the like I really don't think if it's a passenger cargo and hit a bridge pier is going to collapse. But I think you could see the most of these accident what we saw, they are massive. The trucks, they hit these bridge piers. I think they are weight is over 70 ton, is moving 100 kilometers per hour. That means it's moving 30 meters per second. The momentum, the kinetic energy in those structures are massive. So I think the miscellaneous structures you had to design. We talk about this one few times, especially when we design the bridges. There are a lot of elements we attach to the bridges. For example, noise walls, lighting poles, throw screens, and the drainage. The noise wall is along the not on the top of the bridge, on the roadside. So we have to design them. There are standards we have to design to follow this one. To the primary the load case we are designing this one is the wind load. I want to emphasize you because when we are designing the bridge, we always focus on bridge gird, bridge beam, bridge piers, piles, and footings, but we don't pay a lot of attention to this. It's a small element in there. Like you will see the later on when we go to talk about sign structures. These elements we designed for one in a 2000 year return period ultimate limit state wind. For example, in the Sydney environment, when we designed that wind speed is 40 meters per second. If I convert that value, roughly it's about 160, 70 kilometers per hour wind speed. That's a massive wind speed we designed. We design very robust structures. But later on, you will see these fellows maybe vibrate and behave differently with the light wind. And all this element connected with bolts and nuts, yeah, they will have a lot of issues, the fatigue and other issues, and they might collapse. Yeah. So while you are driving underneath the bridge, this noise wall or this lighting pole can fall down to the road below. Yeah, I think a lot of bridges the people encounter. I have this experience when I was in Bangkok. I think because of the bridge vibration, the lighting pole when they were fixing on the top with the nut, I think over the period of time, maybe 2-3 years time, when the inspectors driving around and inspect, they can't find many nuts in the bolts are there. There are no nuts. This structure is just sitting on the top. Maybe you have 4 bolts, but you got only a bowl with nuts, only 2, but there are 2 bolts without nuts. It's happened because of the fatigue and other behaviors. Therefore, when you design and detail in this minor element in the bridge, you have to pay a lot of attention because they are small, they are minor. You can't neglect them because they are function, and the chance of collapsing a bridge beam or bridge pier is very rare compared to a noise bolt or lighting pole. Still, like you are driving 100 kilometers per hour, even a small nut collapse from the bridge is vibrating. When it's falling down, when it's hitting 100 kilometers per hour, you are driving underneath, that impact, there's a small nut will, if it is a hit in your windscreen, it may damage. You have to replace your windscreen. Lucky if you are not get injured, because you may not, but still there's a possibility. Because of that, please pay the attention when you are detailing and design them. Yeah, don't just say these are the small element, therefore it's okay. Yeah. And another thing, it's not that easy, because if you design a bridge with eye girder, if you put a two-lane bridge with the 4 eye girders, you have 8 bearing on one span, you can go and inspect. But if you look at the same bridge in a kilometer, the same bridge, if you have this the noise wall or your lighting pole, it's not that easy for you to go and check each and every bolt all the time. You need to make sure that you cover them in your design. And the other thing, the next one, I'm going to spend a little time with sign structures. I think sign structures is another very important element in a highway infrastructure project. It is not part of the directly, it's not connected to sometime to the bridge, but you can see this highway infrastructure, they were going across the highway. The people are driving all the time underneath that, right? So I think there are a lot of you can have a sign structures, you can have a toll gantries, you can have a portal frame kind of sign structures, you can have a cantilever kind of a sign structure. There are many types. So when you design and you place in them, you have to design them a very special way. I think in the recent years, they noticed a lot of sign structures collapse and a lot of accident happen. You can see this cantilever sign structure collapse. There's another one is collapsed onto the driving car. I don't know the condition of that person inside the car. I think they noticed the failure because of the sign structures. They found most of the sign structures the build, and during the service, the bolt, you can see the crack in here. The bolt crack, and then the sign structure you design with the 4 small bolts, and this bolt crack and it's becoming unstable, and then it's collapsed. So this is quite risky. There's a massive risk you are posing to the traffic. So you have to design your sign structures properly. I think the sign structure design philosophy and criteria has been changed significantly. Now the sign structure design, you design for the heavy wind load. In the same time, you design sign structures for the fatigue. I think a special design code developed by AASHTO. Most of the countries, they use that one. So when you are designing the sign structure to the strength, we design for 1 in 100 year ARI. The one reason why not 1 in 2000, because the sign structure design life is normally much less than the with structures. Sign structure design life is like 40 years. And if it is not, if it is a 1 in 1,000 year also, we consider if it is, there's a risk of collapse into the road. If you put your sign structure away from the road, even you can use a less return period, because even if a sign structure collapse, it's not going to affect, there is no risk for the commuters. So the SLS design wind speed is 20 ARI. This design, you can get your sign structure dimensions, your steel members, all those things you can design. But sign structure detailing and design is governed by the fatigue. And the most of the sign structures after fail, the lot of research they conducted, they noticed that the sign structures fail because of the galloping. The galloping, to the large amplitude, the resonant oscillation in plane normal to the wind. The wind is going there, perpendicular to the traffic plane, is like your screen is vibrate in the vertical direction. So that caused one form of failure. And the natural wind gust, it's not a heavy wind, like I mentioned, that noise fall in the bridge in a slow wind, but it's created the condition that vibrates significantly at that induced vibration caused the failure. And the truck induced gust, because if you see this one, every time when the truck goes underneath, is close to this in here. And here, for example, if it is a sign structure, there is the vacuum created in between, so that creates the lot of the force, because you can see amount of trucks just passing underneath the sign structure. It's significant. So because of that, this recent incident, I think the AASHTO developed the specification for structural support for highway sign, luminous and traffic signals. This one describe how you're going to detail, how you're going to check your sign structure design. Especially the fatigue design, they describe how to detail them. So I'm not going to discuss this one in detail, because I'm going to discuss with you what is the fatigues design latter part of the presentation. When you design the sign structures, we control the camber, and we make sure, because sign structures, the cantilever structures, we don't let that one to camber into the roadway. We always design with during construction stage, we put the vertical camber. Upward camber. Upward camber. Can you please, can you someone, please, can you switch off the mic, please? And we design and we construct with the upward camber to make sure that when its bill is rotate, it's not going to go into the highway clearance envelope. The sign structure design, therefore, please make sure that you cover this fatigue design part. It's very important if you not design this one, because like, for example, if there's a heavy wind like a typhoon condition, I think there's a very less traffic on a highway, right? So even if a sign structure collapse onto the road, there's the chance of hitting that one of commuters, the safety point of view, it's the possibilities are less. But if it is a fail on a normal condition, while you are driving, you don't know, there's a very light wind. Yeah. So because of the fatigue failure under the light wind condition, if this structure collapse onto the roadway, so that is not acceptable. So that is why you need to pay big attention to your sign structure design in the fatigue design. So this code describe in detail how you're going to detail, how you're going to check each and every element in the sign structure design. I will share this design code with you, then you can look at in detail. Then I'm going to jump into this extension of the sign structure to the fatigue design. This is very important. When you design a bridge, you need to understand the fatigue design principles, because you have to design your bridge for the fatigue. I think we learn what is fatigue is. Fatigue is always the resulting from fluctuating stress. The bridge is going to, are they going to subject to fluctuating stress? Yes, because you build the bridge, you got a dead load, your superimposed dead load is there. There are traffic is going, passing all the time. Every time traffic is going over the bridge, your stress level in the bridge will go up and down, up and down, up and down all the time. It's depend on the number of traffic, the location of your bridge, so many aspects. So the fatigue damage is resulting a fracture caused by the stress, because when if there is sometime due to the imperfection of your construction or your material itself, if there's a very minor crack in your materials, maybe concrete, maybe steel. Steel is quite prone to the fatigue failures, and then that will propagate over the time, and the collapse is, as you can see in this bridge. Another thing you saw in all the sign structures. Therefore, fatigue design is really important. The fatigue design is it may be due to a load, for example, the traffic load. It may be due to the distortion, like in the galloping and the other, because of the wind. And there's the movement of the structures like vibration. It causes the combination of both, or either one of these. And then, as I mentioned here, the traffic load, when we is produce a moving load, therefore is produce a reversal of the fluctuating stress, then your structure is prone to fatigue. Then you need to design for fatigue. The wind loading also causes fatigue. Of course, you saw that in the previous slides, when you design a sign structure. But if you design like a cable stay bridges, if you design the bridges with the stay cables, I think the wind loading causes a significant impact on your especially cables and other thing. I think that causes the fatigue. So you need to see that one, because these are the special conditions. Like when you attach your sign lighting pole onto your bridge, that causes the wind induced wind loading causes the fatigue. Yeah, it's similar to the sign structure. It's a part of your bridge, because you have your bridge underneath, you got the roadway. So then because of the fatigue, if your lighting pole collapse either to the bridge driveway or to the road, so you have a similar issues. Because of that, you need to make sure that you design now. Then the fatigue sensitive structures, we should design with the ductile material. For example, now for example in Australia, we don't use the high strength bolt to design the sign structures, and we don't use the high strength bolt to design the anchor bolts, because you can see the high strength structures, the less ductility. You will see that one in the later on the presentation. You have the crack, and then it could fail. You need to, your selection of material is very important. I think we see later on the next slide, when you increase the number of cycle, you increase the number of cycle, your fatigue strength will reduce. I think you learned this one. Normally we define the fatigue strength for 2 million cycle. That is we call when any element subjected to 2 million stress cycle. At the end of the 2 million stress cycle, what is the strength of that particular material, or joint or bolt or well joint? We define that one as a fatigue strength. You will see in the next slide. And as you all know, the steel element and welding are very critical critical in fatigue design. And the concrete bridges are not that critical, but you had to check for your fatigue stresses. You had to check that one. You can't just neglect that one. Especially the thin structures with thin web, there's a possibility of fatigue failure. It's very rare, but you need to make sure that you design now. This is the slide. So the fatigue, the stress versus the number of cycle, we call SN curve. You will learn this one when you are studying in your bachelor degree. Any material, the higher strength can carry the steel ultimate limits ultimate strength. Then when we were designing it, we work around yield strength. If it is a steel, we know until then we got a steel strain curve, the linear variation. And then we just keep, when a structure is subjected to fluctuation, reversal stress, your number of cycle is in order of millions. We talk about 2 million cycle. then the higher the number of cycle, you can see in this line, the fatigue strength is reduced. Please note that this is a model developed to design. The exact behavior is not same. If you do experiment, you may have a lot of dot point around this graph. So there is the number of cycles. You can see at the end of this one, you got a flat curve. The strength won't reduce significantly. That strength exactly the same. We call that is the fatigue strength of the fatigue strength of the material. And you can see when I extend this line across to the stress line, you can read what is the stress corresponding to that. Yeah. And on your left-hand corner, you can see I mentioned infinite life fatigue. What does that mean? Infinite life in the sense you can have any number of stress cycle in your structure. It's not going to collapse because you design, you make sure the fatigue stress in your design is less than the fatigue strength. Therefore, it can have an infinite life. So, but normally when we design a structure, we are not going to go there. We are above this point. We call the finite fatigue life. What is the finite fatigue life? This is the fatigue strength of your material. For example, when your structure is subjected to N1 cycle, let's say it's a 2 million cycle, the strength of your material corresponding to 2 million cycle. Let's say when you read this one, for example, on a structural steel member, let's say 120 MPa. 120 MPa is about 50%. 130 MPa, about 50% less than your yield strength of the structural steel member. So then in this area, that means if your the stress on your structure and the number of cycles, it is a finite fatigue life, because if you exceed the number of cycle in your structure more than 2 million, for example, in this one, right? If your structure will exceed the fatigue strength. Is it clear? Because you're going to exceed your stress in your structure. The fatigue stress in your structure is greater than the fatigue, the strength corresponding to this N1 and sigma 1. So then your structure will be failed. So when you design your structures, you need to make sure that you design your structure, your fatigue stresses always on your left-hand side of the curve, not on the right-hand side or below the curve, not above the curve. You need to make sure. I think you can see in this diagram, I have a lot of sigma 1 and N1, sigma 2 and N2, right? Those numbers, right? Why I have those numbers there? Because when you design a bridge, like, so you have a very big trucks going on the bridge, right? That produces a significantly large stress on your bridge. But you can have a small car going on your bridge. You can have a different stress in the smaller stress level in your bridge, right? So that you're going to have a fluctuating stress on your bridge. So that have a cumulative effect in your bridge. And to take that one into account, there is the way there's a fatigue theory we call Miner's rule we use in the fatigue design. What the Miner's rule say, if your stress level is, your bridge is subjected to various stress levels over the period of time, and if you get your stress reversal, for example, sigma 1 stress reversal happen, the number of stress cycle is N1. The sigma 2 stress reversal is number of stress cycle is N2, and so on. So then the fatigue design is based on the Miner's rule, or else called damage summations. You go to your stress is sigma 1. In the fatigue strength curve, you draw the stress line. The corresponding to sigma 1 stress level, if your structure can go up to maximum number of stress level in your fatigue curve is N1. Similar to stress is sigma, stress level various sigma 2 is N2 and so on. So in your minus rule, say you get the percentage N1 over number of cycles over strength. Those number of cycles, if you add them together, if the summation is less than the 1 or 100%, your structures are still in the same. I can give you the classic example. This is something like we design bridges for the lighter load, and we let the bridges subjected to heavy load. Over the period of time is subjected to different kind of a stress level. If you want to check the condition of your bridge against the fatigue, you can use this principle. Yeah. Another way, if I explain it to you, let's say you build a bridge with, there's a small crack initiate on the bridge. That crack will propagate because of this reversal stress cycle sigma 1 to certain percentage. Sigma 2 will propagate by certain percentage. It will add up together. At the end, there's a point that it can't sustain anymore. Your bridge will got a brittle failure. To prevent that one, we check that. But when we design the bridges at the early stage, we make sure that we detail our structures to satisfy the fatigue design. Is it clear to you what I explained in these 2-3 slides? Before I jump into next slides. Is at least clear to you the fatigue damage is resulting from fluctuating stress, the traffic load, for example, and the fatigue, the fluctuating stress, higher the number of cycle, the fatigue strength will reduce. So experimentally, we define the strength curve. Then you can calculate corresponding to number of stress cycle. For example, 10 to the power 4 and 10 to the power 2 million cycle is our standard one. You can calculate the fatigue strength for joints and everything you're going to see next. And then you compare that one against your actual stresses in the structure. That is how we're going to design for fatigue. And if a structure is subjected to series of reversal stresses over the period of time, we use the minus rule using the cumulative damage method to assess the structure. So that is something like you calculate the percentage of damage caused by each and every stress cycle. This sigma 1, 2, 3, 4, 5, so on. And this is one example.
Yeah.
So
Rohit, I can add to that, Rohit. We design pavements like that. Fatigue. If you get those road design guide, you will have the same equation for pavements.
But yeah, to make sure that the concrete strength is below
fatigue,
the
minus hypothesis. We use minus hypothesis for the fatigue loading.
To get the cumulative damage in the pavement, right?
Cumulative damage in the pavement. Yeah, good to know that bridges are designed the same now. That's good. Thank you.
Thanks, Pratap. Yeah, these are the you can see these are the detail categories they call. I think if you go to different design standard, they have a different, like for example, ASHTO, they call this one A, B, C, D, like that. And then this is based on the Australian standard. You can see on your the stress range, the fatigue stress range is going from 20 to up to 500. And you can see this line detail categories. That is the different details you will see in the next page. And when we were, you can see this number, for example, the 100, the fourth line, this curve is crossing the 100 stress level at the 2 million cycle. So if you read this one, this the strength limit, this the detail category 100 mean the particular, the welding or the welding detail, basically the fatigue strength for the 2 million cycles is 100 MPa. You can see if you go to the left hand side of the curve, if your number of cycle is less than 2 million, you see your fatigue strength is higher. If you go more than 2 million cycle, it's going down. Yeah, because higher the number of cycle, the strength is going down. These are the logarithmic curve. Because of that, this they make it to linearize for the design purposes. These curves you need to read all the time together with these drawings. You can see the one of the picture. I think when you were designing and detailing, especially the steel structures, the welding, for example, on this picture, you have the detail category 112. So if you see this drawing in here, this is the third line here, that's 112. During the 2 million stress cycle, the fatigue strength of this particular welding detail is 2 million cycle. This welding detail is quite common. So if you want to build the bridge, the length of the bridge is, let's say the girder is 25 meter. You can't produce a 25 meter long plate and bring here. The plate length will be maybe 6 meter maximum. Then you weld them together, pieces together. Then you get your required length, 25 meter. Then you have always you have this weld across. So when you have this the bridge, if you put the simply supported beam, if your girder is on the bottom, your tensile stress in the bottom flange is tensile stress in the bottom flange because of the stress reversal will fluctuate, right? If we have a welding detail like this, corresponding to 2 million stress cycle, you can have a maximum stress reversal. For example, I will give you the word, the stress, tensile stress in your bottom flange due to that the traffic load should be less than 112 MPa. Does it make sense? Because if you get a simply supported beam, the bottom flange will get the tensile stress, because the bottom flange will get tension, the top will get compression. Then your fatigue stress, you need to make sure that when you check your design, according to the location of the joint, it won't exceed that value. But it's depend on the number of cycle. If it is a 2 million cycle, it's 112. But if you design your bridge, you are designing your bridge only for 1 million cycle, so then it's a different story. You can have a higher stress, higher the stress limit. So this 112 is corresponding to 2 million. Like that, if you go to any design codes, you have all the welding details defined. This is, for example, in a column. When you are producing a column, you get a piece of plate, you bend, roll that one, you weld vertically, longitudinal seam, and you get a crux in here because of the fluctuating load. Because of the axial stress in the column, it will be fluctuating when the traffic is passing on the bridge. So this stresses you need to calculate. So in addition to that, when you were going to do with the fatigue detailing and design, you need to make sure you follow the design code, you detail that one, you make sure during construction, you tested and you confirm your design is working. You make sure that your quality assurance system put in place to ensure that your weld is right. Yeah, for example, in here, if you get a 2 I-beam and if you connect together, if you weld around this, the full 2 I-beam, if you full penetration weld in around the whole, the perimeter of the beam, you can see your strength of the beam. If you use like a 350 MPa structural steel, but your fatigue strength is only 112. It doesn't matter your initial parent material strength, but still the codes give you based on the number of a stress cycle. I will show you this one. This is the exactly what I built when I was in Bangkok. This is the real steel construction. And this is the steel fabrication yard. You can see the one girder on the top. This girder is 50 meters in length. You can't bring the plate in a 50-meter length. They are 6 meter in length. We just assemble them together, weld them together. You can see these guys are doing welding, doing all the fabrication work for the eye girders. You can see I have clearly marked the location where the places they do the butt welding. They assemble these steel pieces together. So when you build this bridge, when you allow the traffic, so you need to, this bridge, the bottom plan is a simply supported girders. Because of the fatigue loading, there's a stress reversal vary from 0 to at the support to the maximum at the near the center area of the bridge is keep varying. So you need to make sure that where you put your well joint, you need to make sure that your fatigue, the fatigue strength is not exceed this allowable or fatigue strength. Is your your stress reversal due to traffic load. I'm sorry, your stress produced due to traffic load is less than the fatigue strength given in the code. Yeah, you need to do that check. For example, you see the picture on the bottom. You can see this, there's the bridge is coming behind. It's going to go across, it's going to support by this cantilever element on the top. The other cantilever section in here is merged with the ramp. Yeah, this is supporting another bridge. It's a ramp on the left-hand side. The right-hand side, the bridge is in the different level. So you can see we get this box section and weld to this column in here. You can see whole bridge is cantilever, whole traffic load is cantilever, is produced significantly large bending moment in here, significantly large stress in here. If you not properly detail and design, because of the fatigue, the structure will be come down after 20, 30 years later, nobody knows. People are keep driving it, right? Because you not go and inspect this thing, you can't see this from the ground. There will be cracks in here, this will come down. You need to make sure that you design these structures and detail in a way, all the element you detail and you make sure that you design that one for your fatigue loading. And then this is what, when you are designing the difference between the steel bridge and a concrete bridge, the main difference is the steel bridge design. That is why it's not that easy, because the design itself is quite challenging. And in addition to that, the design detailing and the fatigue design is you have to go in a lot of detail. You will realize the amount of detail you need to go into when you design for fatigue in a steel bridge from this particular drawing. You can see this picture in here, this column, this pier head. If you go to this here in the back, you can see this behind you, this pier column is fabricated. This is this column fabrication in the side, in the yard. You can see this vertical column is fabricated. It's already finished. You can see in here the people are doing welding, and yeah, they are doing checking and then doing welding here. But you can see on your left-hand side, this is the detailed fabrication drawing, the expanded detail of the fabrication drawing we produce to make sure that all these hundreds of elements we cut and we assemble them together in the site, all by welding. So when you are detailing this bridge and when you let this element to be in service, you need to make sure that you would properly design and detail this whole structure for the fatigue. Yeah, it's not that simple and straightforward. I will give you a very simple, the example, the pipe section, the column section. You got the piece of paper. If I could give you the exact number, this one, the width of this the plate will produce the height of the column, because we get this plate, we roll and we put the vertical seam, the weld in here, full penetration welding. You can see we roll this one, we get a 2.2 meter height column, and we assemble them together, we get the right column height. And then 2 piece, 3 piece, sometimes 4 piece, we need to get the required column height. And then we weld them together. We make rings first with the seam, vertical seams. And then we place them, the vertical pipe stack on top of each other, make sure that these seams are not coincide with each other. They are placed in different location to make sure that this seam is not continue from one, there is no seam continue from top to the bottom. So they are staggered. That's the way we make sure that it's not going to go all the way across. These are the small thing. We make sure that we properly detail this structure and fabricate, and we build them. So it's not simple and straightforward to explain it to you, because I give it to you the extent you need to get into understand this one and to detail, but they're not difficult, because if you go to the design codes, so they give you this weld in detail, right? They give you the stress level. You know your number of stress cycle. Let's say our stress cycle in the bridge is 1 million. You can calculate from the design standard. And then your detail, the corresponding fatigue strength is 112 for 2 million. The 1 million we say is a 50% higher than that one, right? Let's say 150. Then you make sure that your welding detail, corresponding welded detail, these two plates assembled together, your fluctuating a stress or stress due to a traffic load is less than 150. Yeah. That's the way you need to make sure. Another thing, when you detail, you should not put, unless otherwise you have to, for example, in this situation, you need to have this cantilever section welded well to your cantilever arm you need to produce. But you should never have a welding joint detail in the middle of the column in your bridge girder. That is not acceptable. You should not detail that way, because you got a maximum stress at the center of the center of your girder. Then if you put the joint, there is a possibility that that joint, because the risk is really high. Another thing, please remember that one. So you can see the way the people are working around in here is the same any country in the world, because you are fabricating steel girders. Sometimes most of the fabrication happen in the few part of the world. For example, the company I worked before in Bangkok, we have a really big yard. We fabricated close to 50,000-60,000 tons of steel, and they are expert in that one. They know exactly what to do. You should have seen this kind of a drawing first time in your life. This is what they produce. Not now. This drawing produced about 1998 or 1999. Before 2000 is more than 20 years ago. We produced this drawing, and yeah, we used this much of the engineering principle when we were fabricating to make sure that these are steel. Your tolerance are measured in millimeter, because each and every one of these drawing I sign off as a shop drawing, as a designer. I looked at this one. I could remember in by heart as to the fatigue section. If I give you an example, one of the most critical in the fatigue design in the ashto is this welding joint in here. This bottom flange and this stiffener, this is the category F dash. If I give you the number those days back in AST, design standard is 7 kips. 7 kips in the sense you have to multiply this one by 1000. 7,000 divided by 142 is the MPa. If I tell you the number, 7,000 divided by 142 roughly is about 50 MPa. Yeah, one of the lowest fatigue limit, but if you go to the Australian standard, they go as low as 36 MPa. It's about 10% of the steel structural steel member yield strength, about 10%. Yeah, I can explain this on the fatigue design for so many hours, but I just want you to understand the simple, if I summarize this one, the fatigue failure is catastrophic. So you have to design for the fatigue. It's very important. The fatigue stress is caused by the fatigue is caused by the reversal stress in our bridge. Bridge is subjected to traffic. Because of that, so the traffic load will produce the reversal stress. So lie load, for example, so you can use the lie load. You know the lie load bending moment if you divide it by the your section modulus. So you can calculate the stress variation. So you know what is your stress variation. Then if you know the stress variation, in addition to that, depend on the type of the bridge. We discuss this one later when we go to bridge designs. You can calculate from the design standard what is the number of stress cycle corresponding to the particular road type. So you get that number and you go to the design standard. Depend on the type of welding. It may be a butt weld of your plate, or it may be a weld between your, for example, butt weld in the joint, it will be subjected to axial stress. If it is if your weld between your web and a flange, it will be subjected to that. The fillet weld will subjected to the shear stress. Those limitations is defined with the pictures, in the, because you don't want to imagine. You can just go to the correct picture, you select that one, they will give you corresponding fatigue strength. So then you can select what is the fatigue strength. Most of the code defined based on the 2 million. Then there is a weight you can convert. There are equation. You can convert that one to corresponding to your number of cycle. Like we talk about that example, 2 million cycle, 112 MPa, the strength, but my bridge design only for 1 million cycle. Then the fatigue strength is 150 corresponding to 1 million cycle. So then I compare 1 million 150 MPa as the strength against my actual stress. It may be, let's say 80, 90 or 120. So then I know that in terms of the design, it's working. But when you come to the detailing, because it's a well, the well is doing all by humans. Some well now they use robots to do that one. Different conditions, different well environment, and you need to assume those things. The people are welding in a different country, and you can't check each and every well 100% to make sure that it's all covered. It's all depend on the people experiences. You need to think all those elements when you design and detail your well. Some designers, because the codes already give you the minimum thicknesses of the well, some designers, they try to save the 1 millimeter of the well, but at the end of the day, he's creating your stress. Is that 1% saving sometimes affect in terms of the performance, like the 10-15% risk. So you need to see all those things. You need to keep in your mind when you are designing and when you are checking. Especially, please pay attention when you are designing the sign structures. They were cantilever structures. They have a well, because these structures, I think people not pay much attention when they were designing, building, when they were constructing, when they were maintaining, but there's a significant risk posed by them. So please pay your attention. Yeah, I didn't neglect the concrete bridges as well. So I put you this table. if you are designing a concrete bridge, so your reinforcements, your stress level, if you use your normal reinforcement, the 50 MPa we use in Australia, the 50 MPa yield strength in your reinforcement, but your fatigue stress range or your fatigue strength is 150 for 2 million cycle. Yeah. And for the, if you're bent up bar, if you with the bar with the hook, that will reduce a lot, because this is a lot of people talk about this one, where the concrete bridges got a lot of issues with the fatigue, where you have the shear stirrups and your stress level go down to 68, right? If you go to pre-stressing wire, your fatigue stress range is 150. And I have example in here according to the Australian standard. If your number of stress cycle is in this case is only 1 million, so they 10 to the power 5, 200,000. If your number of stress cycle is 200,000 in this particular bridge, and then your stress, the strength in that curve, if I go back to here, in that curve, we go this way. We go this way, we have a higher value in here. That magnification, you can calculate using a factor. That factor is given from this formula. Different code have a different equation. Please use this one. And then your magnification factor is more than, is almost 200%. Then you convert that one, you can see your fatigue strength is quite high. The fatigue strength is quite high. For example, for the reinforcement is 323. This is quite high, because when you design your ultimate limit state condition, you use the 0.87 time the whatever your yield strength. So it's close to that value. Therefore, your fatigue design is not that critical, but still you need to have this table developed by yourself. You need to keep these papers on your side when you get your stress outcome along your girder design. You a different section, your stresses, when you calculate along your girder, you can easily compare this one against these numbers. Then you can say that your fatigue design, you met this one. The concrete structures fatigue design is not as critical, not as cumbersome as the steel bridges. So you're lucky if you design steel concrete bridges, but steel bridges is a lot of fun. It's a lot of fun, a lot of challenges when you design steel bridges. Yeah, and yeah, it's a lot of challenges if you design that one, because they are slender structures. Yeah, everywhere I got a buckling and so many complicated formulas. But if you understand the behavior of the structure, that to correlate them is much easy. But if you do your design based on formulas, I don't think you can do a proper bridge design.
So Rohit, with respect to steel design on fatigue, is there a relationship with the curvature? Now, say for instance, if the bridge is curved, based on the curvature, whether there's a reduction in the fatigue, allowable fatigue stress.
See, in the codes, I think they don't have this relationship they develop. But the only thing, if you have the curvature in the bridge, like I think then the stress reversal you get a structurally, because for example, if like arch, you get a lot of compression in there that will structurally be treated. But if you answer to the question, yeah, I think as far as I know, I think there is no special consideration given for the curvatures of the because the curvatures in the bridges, we of course we have a curvatures. For example, this steel bridge, the 25-meter long, this bridge, we fabricate this bridge with the 45-millimeter camber in there, built into that one. During construction is going to flat, but in terms of the fatigue design, no, we don't, as far as I can remember. Yeah, there is no.
Thanks.
Yeah, I can check if I can find any
There is
research paper or anything.
some research paper, something. Please let me know, because I have a similar issue with the structure where the reviewer is asking for this reduction.
I can check the design standard and have a close look. If there is a clause in there, I can send it to you, because I think the curvature in the bridge, it's not the one, because it's the reversal stress in the structure that causes the fatigue. Yeah, I can check that one for you.
Thank you.
So I'm going to quickly run through the material section of the this one, because they spent more than close to 2.5 hours in the previous sections. The common material we use in the. Sorry, I forgot to ask any question about the fatigue design. Anyone need any clarifications? Okay, then I'll continue. And then the common material we use in the concrete design as the bridge construction. So common material are concrete, steel, and the strands. So I'm going to discuss about these three material, but I think all of you are quite familiar with this one. Please bear with me, because the numbers I'm talking about is the cylinder strength, but in Sri Lanka, what you are using is the cube strength. So I'm going to put wherever possible the cube strength within the bracket. The conversion factor is 0.8. For example, 100 MPa, the cylinder strength in terms of the strength, check the cylinder strength, the failure before the cube, because of the cylinder strength is less. So if you convert that one to equivalent cube, the strength is the you have to multiply by 1.25. For example, 40 MPa cylinder strength is corresponding to 50 MPa cube strength. So if you get a concrete, the concrete can carry a high compressive strength, but it can carry only very the low tensile strength is about 10%. In the bridge construction, we use concrete from 25 MPa to 100 MPa. You need to be mindful when I say this statement, you have to read in your design standard. For example, this is based on the Australian standard. If you go to British standard, sometimes it may be ASHTO, maybe higher range, or maybe a little bit less in terms of the higher steel strength. Like for durability reasons, most of the bridge construction, we use more than 40 MPa. Another important parameter in the bridge, the density, when we look at the bridge density, there's a significant variation of the density of the concrete. It's vary from 2.1 ton per cubic meter to 2.8. Another thing all of you know, this the famous stress strain curve, and the ultimate limit strain of concrete is 0.3% for ASHTO and Australian standard, but British standard and a euro is 0.35%. I use the percent to easy for me to write, because I multiply this one by 100, then first two decimal zeros will be go, then 0.3, 0.35, something like that. That's what I'm going to talk to you. And as a concrete, as a material, so it's got a Poisson ratio 0.2, and the thermal expansion coefficient 1 in 10 to the power minus 5. I use this one something like that, 1% millimeters per meter per 1 centigrade. This is the way you need to remember. If you get a 100-meter long bridge, if you change your temperature by 1 degree, right? That is 200-meter long bridge. If you change your the effective length for the expansion or contraction is 100, If you change your bridge temperature by 100 degree, your bridge will be, dimension will change by 1 millimeter. Yeah, this expansion, the coefficient of thermal expansion is very important. Even for your structural modeling, the Poisson ratio is important. And the addition to that, the concrete Young's modulus are important. I have this table, Young's modulus, the ways vary between for the various different concrete type, right? So if you use the British standard, you can calculate them. In addition to that, I have another important design parameters we use, the flexural tensile strength and uniaxial tensile strength in the concrete. This is based on the ASHTO and Australian standard. These values are tabulated. You can calculate using any standard. These are the main parameters we use in our bridge design, the verb. So and when you go to the, when we go to the the concrete element, these parameters we're going to use in our design. So concrete we're going to use mainly for the compression, to carry the compression, not to take the tension. Give me one moment, 1 minute, please. Sorry. Yeah, now the concrete we use for the mainly for the compression, but yeah, that's quite, everyone know, every structural engineer knows about it. Yeah, when we go to the reinforcement, reinforcement is we can use for both tension and compression. And I put here nothing much information in here. I put the stress strain curve of the reinforcement bar in here. This is normally in Australia we use 500 MPa yield strength concrete. I'm not sure in Sri Lanka, like you might use 490. Is that right? 490 or is less? 410. What is this reinforcement yield strength you use in when you design reinforced concrete structures? 500. Yeah. And I can see I have this 5% strain range I mark in this one. So normally when we design the bridges, we don't use the reinforcement if the ductile range is less than 5%. Please remember that one. So we have to use the we discuss about the ultimate limit state behavior of the ductile failure of the bridge. So you have to use the ductile material. So the minimum ductility in the bridge, you need to make sure that you are in the 5% range. You will find the steel less than that. And the good thing about the steel is you get a linear stress variation close to the yield strength. Another thing, when you are designing a steel, when you are using the reinforcement, it's better to understand these points shown in this one: the proportional limit, elastic limit, the yield point, and the ultimate point, and where it's going to rupture, because the reinforcement have a significantly larger stress range before its rupture. And another thing, I put this curve in here. If you go to various design standard, you will going to see later on next couple of slides, they develop the different model. For example, you go the linear, the variation, and then from these point proportional limit, the elastic limit to the yield point. That one, sometimes some design standard have a joined by a straight line curve. and then all this, beyond the yield strength, you use the horizontal yield plateau in your various design model. Please understand that one, these one more or less, they try to represent the actual model, but if you really want to design a structure, if you want to check something, now you can use this actual stress strain curve in your structural modeling. For example, most of the softwares facilitate that one. Now you can use that one, you can input that one, but it's not really required that much of accuracy when you design a bridge. And these are some of the information about the bridges. This is the common type of steel. We use 500 N. Grade N is the the ductility, high ductility range steel we use, but we never use the L for bridge design, because especially when the bridge is subjected to earthquake, we design for that one, we don't use the low ductile reinforcement. You can see the uniform yield strain range, 5% again 1.5%, again 1.5%. So this ductility is really low. Because of that, for the earthquake design, we need to detail and design the structure with the higher ductility. So we don't use that material. Because of that, please remember when you are selecting your steel, it's very important. Then I'm going to because you all familiar with this thing, I'm not spent so much of time in here. And then this one, the strand. I have this, I try to get this one, find put all the curve together in the same page for you to understand. You can see on the bottom, you got a steel with close to 500 MPa yield strength. You can see the yield plateau in here. But when you go to the top, like the 160 MPa pre-stress strand in here, you can see it will rupture even before it's reached to 5% yield strength. And normally you can see this line I draw here, this is where we are working when we were doing the designs. And the design parameters, I think when we were working with the strand, we always talk about breaking point, and then we define the yield strength based on the proof stress or the 0.1% strain. We define what is the yield strength. This value is vary again. It's normally is 82% breaking force in the Australian standard, but in the ASHTO is 85 to 90%, but BS is in between, I think. I forgot the number, I'm not sure it's 0.87 or not. It's divided, yeah. Someone can help me with that one. And the other thing, the common type of the strands we use in this bridge construction is the stress relief, the 7-strand wires. I'm not going to go in this detail. I put this one, the wires is vary from 9.5 to 15.2. There are some strand with 15.6 as well. And the common type is 12.7 and 15.2 in the bridge construction. Their area is 143 and 100 millimeters. And the breaking strength, that's where we define, is quite high, 18,700 and 18,030. These are the common factors. I think, yeah. So structural engineers, you know these values. Even if you go to catalogs with the suppliers, you can find those values. Yeah, there are steel strand. You can use the area as large as 150 millimeter and even larger than that. But in the bridge construction, we won't go beyond that. Then I have this, the stress strain curve model we use in the bridge construction. When we were designing reinforced concrete structures, you can see in the ASHTO and Australian standard, we use the parabolic curve, and the approach used in the British standard and the ASHTO and Australian standard is a bit different. There's a significant difference. because when we were using the Australian and Astro, you got the stress strain curve box, you got your ultimate limit state concrete and 85% of FC prime, whereas when you go to the British standard or Euro code, it's much less, 0.67 FC prime divided by the gamma m is 1.5. So these curves we used to when we were analyzing when we were designing the concrete members. I just want to highlight you what is important is this a strain. Yeah, this a strain. So we say in our concrete element, we won't exceed our strain limit more than 0.3% or 0.35. And we have a two different curve for the ultimate limit stage and serviceability limit stage. Similarly, we have a similar curves for the steel, but the steel one quite easy because the linear variation we can expect in the steel, and then because of that the Australian and Astro use the linear variation up to yield strength, then we use the yield pattern, right? So you can see you can go to a strain after reach the yield strength, you can keep going. It's not a problem. Mathematically, you can make it, but whether in performance wise it's going to work or not, you need to be mindful. Then the material stress in this strain, I will spend some time with this one. Like you can see in the stress strain curve, yield strength we define the point somewhere here. Then the break-in point, we go to somewhere here, and then we got a flat yield plateau. That is what this curve represents. This is based on the Astro and Australian standard. It's go up to your certain extent. This is the 0.8 times the breaking FPB. That is the value, the linear variation. And then from there, 0.8 to the breaking stress, you got a different gradient, it's much more flat. And then after that, flat. You can increase your strain, but your strength won't increase. But we never design our structures in this area. This is what important for you to understand. Suppose if I don't have much time to explain too much, because can you design you can design the reinforcement with concrete. You can design reinforced concrete element, right? You can see your reinforcement yield by 0.25%, but your steel the concrete will fracture at 0.35. So it's make sure that, okay, makes sense. Then your concrete, your reinforcement, you can design yield before your concrete is fractured. So good. Can you do the same thing with the strands? No, you can't, right? You can't. So you can see, because when your strand is close to the 80% of the breaking, close to the this linear proportional limit, or close to 80% of your breaking load, you got a 0.7 the strain. Your strain limit on your strand is 0.7. So therefore, if you use the concrete and strand together, you can't get much benefit, because when you fracture your concrete at 0.35 level, your stress level in your strand is way much lower than your capacity of the strand, what you can achieve during the construction. That is what people do, pre-stress concrete. That's what the people back then, about 50, 60 years ago, the president, he thought about using this wire in a proper way. These things developed with a lot of experiment and with a lot of experience and a lot of bridge failures, and all those things experience come together. Now we are enjoying the benefit. You can see this the point in here is missing there. Okay, the breaking stress is 130 in this curve. Then normally we put when we develop produce the reinforced concrete, pre-stressed concrete section, we stress our concrete element up to 75% initial stress. So you are here in your dot point, 75% of your initial stress, that is 173. So you are in your red point, right? Then after that, because of the creep shrinkage, all this relaxation, you know, the stress in the strand we call pre-stress loss. If it is a 25% of the loss, over the time, this stress level will go down to 75 initially, go down to 53% approximately. Then the stress level will be 129. You can see now this is your stress level in the concrete. This is your strain level. Then when in the service, when you loaded the bridge, when it's subject, because the bridge life is 100 years, this creep shrinkage, all these losses will happen within a couple of years in the bridge. You are in this blue point. Then you can see your bridge with the concrete, it can get a 0.35% ductility range. That push will allow your bridge, your strain to develop more strength, and you can come up to this pink point. This is the arrow. This blue point to pink point, it can be vary according to the load on the bridge. But you can achieve the maximum the capacity based on your losses. I think these are rough numbers, but what I want to tell you, this is the way the pre-stressed concrete members behave. This is how you need to understand when you are designing a bridge. You need to have an understanding about where your strain limit on the pre-stressed strand, your strain limit. Because if you just go beyond this point, your strand will break. That's the reason I have this dot point, this vector diagram in here. Is it clear? Yeah, the same thing. I put this stress strain curve for your reference for the British stand based on the BS code. I think you all familiar with the British standard better than me. I've used this one about 30 years ago, and the stress strain curve we use in the design. You can see that one in the British standard and the Euro code. These model we use a very lower stress level in the design. So the same story about the strand, but bit different, because now initial stage in here, and then we go down to the stress loss here. Then you can see we are in the plateau line during the ultimate limit state, but you can see the stress level limiting to 1591 is different. If you get the 830, 1830 is the capacity, the breaking load, but it's the your maximum stress you limit on your strand to 87% of that value. I think is gamma m is 1.15, 1 over 1.15, I think 87%. Yeah, when you design based on the BS and Euro code, this is the way the stress pattern is going, but you can play with your strain level. But in here, you can go to any number. You can draw this vector. You can change the angle, whatever the way you want. All right. Then to close with this presentation, I'm going to present you a actual bridge design. The girder is 34.1 meter length. The span between the girders is 33 meters. This is one of the standard bridge girder we use in the bridge design. The Super T girder, the depth of the girder is 1.5 meter. The deck is 200 thick. We designed this one as a composite a structure. I'm going to give you, present you what is the ultimate design capacity of this member when we calculate using Australian and the Australian standard and the British standard. The reason I want to explain it to you, because you are using a very different kind of the design model. Your behavior of the concrete and the steel, you assume totally different way in these two standards, these three standards. So, but still you can see your design outcome is more or almost the same. We designed this bridge. This is the ultimate limit state capacity. The reason you have this jumps in here because of debonding, and you can consider only the flat line on the top. When you calculate the ULS capacity of this girder based on the Australian standard is 19,100 kilonewton meter. The strength of this concrete, the deck is 40 MPa, the girder is 50 MPa. But when you calculate the same one using the British standard, don't worry about this curve on the bottom. That is, I just put to give you some idea about the actual loading. You get 20,035. The reason is this one, because when I was calculating this capacity, I make like apple to apple, because the concrete strength, you can see in here, for the cylinder strength 50 MPa, I convert into cube in strength 62.5. Similarly, the deck strength 40 MPa, I convert into 50 MPa. When I'm checking the British standard, I use the concrete strength, the cube strength 62.5 and 50 MPa. And if I use the same concrete strength, I notice the actual capacity less than 5%. When I change the other one, change to the equivalent cube strength, the capacity I got about 5% higher. What I try to say, when you design this one in a real term in these two codes, you get the same outcome. So the more or less the same. There will be a very minor change. There's no significant difference. So, but you are using the totally different extreme, totally different design models, especially in concrete. You're using the parabolic behavior, but 0.85 FC prime against much lower value. Like you can see the British standard, we use the value is more or less less than a 50% of the concrete strength. And when you were designing, the final outcome of your design, more or less the same. Yeah, because of that, there's no rule that you can say I use the one standard EQ better results. No, you don't want to think like that. Another thing, you can use a different design standard to get the same outcome. But the only thing, when you are using different standard, please make sure that the bridge design, you can't mix the design standard together. The reason is when you design the bridges, the design standard we have, we got the loading associated with that one, the bridge design loading. Yeah. Any question with that one? Yeah, I don't think you all really good with the reinforced concrete and the pre-stressed concrete design. And I'm really going to spend about another 10 minutes to touch base with the bridge loads. Okay, the bridge loads. Bridges, we are designed for the traffic. You can see on this top two pictures, the amount of the trucks on this cable stay bridge, another one, the bridge across the river, amount of different kind of trucks and then cars and so many kind of vehicles in there. So we are designing a bridge for the traffic loading, but that traffic, you don't know how it's going to behave, how much is going to there, how you're going to estimate that one. Yeah, that is one of a big question when we were trying to get the bridge load. Traffic load is very hard to predict, and then but still you have to design to bridge to satisfy certain kind of load with a lot of experience, experiments, and so many things. The many design standard come up with different traffic load models. Yeah, these model, there are significant variation. If you go to ASTRO against the Australian standard, go to British standard, Euro standard, there is a, you can see noticeable differences for the traffic load. The other load, like a bridge, the bridge we designed with the concrete or steel, there is a dead load. Okay, of course, we can calculate that. And after we construct the bridge we design, we're going to learn this thing in detail later. Bridge we construct in element, like in the bridge deck. To make economy, we design bridges, deck and the beams combined together like a composite element. We call, after we construct the bridge deck, after bridge deck becoming a composite section, whatever you construct after that, we call those things superimpose onto the bridge deck. We call superimpose dead load. For example, bridge barrier, the bridge deck, drainage, and anything you build after the deck is hardened on the top, construct attached to the bridge deck, we call superimposed dead load. Another one, of course, the wind load. We talk about at the beginning when we design for the wind, ultimate limit state condition, we got a 1 in 2000 year return period, but SLS we got a 1 in 20 year. And again, we had to design for the flood. So the flood effect, if you not design for the flood, so the bridge is going to, you can find a situation like in this picture. In addition to that, you can see this, the fluctuating load. This is the earthquake load. This is something you can't, this accidental load, you can't estimate, but you have to design. Similar to the traffic load, you have to have some models to design for earthquake load. So these load, some load you can superimpose dead load, and these things we can easily calculate because we know dimensions, we can estimate them, we can calculate. But traffic, because the bridge is servicing for different traffic, but you use different traffic models. Traffic, wind, flood, earthquake, all these loads are loads we develop similar to that the stress strain curve we use for concrete design. So these model loads we develop a different standard define these loads. So therefore, don't try to go and try to estimate equivalent traffic load to what is in a particular design standard. But when you are designing for road authorities, when you are designing the bridge for particular load, but you can ask the designers and contractor to test the bridge before we open it. There are some bridge tests they tested. Yeah, you can do that one to see how it's going to behave. And any questions here? Okay, then when I get the loads on the bridge, I categorize into mainly 3 segments: permanent load, transient load, and thermal effects, and the construction loads. And the permanent effect is a permanent load, dead load, superimposed dead load, earth pressure, of course, water buoyancy and thing, and creep and shrinkage. Yeah, pre-stress, differential movement, because these are the thing in a bridge. The bridge is always, the law members is always subjected to deformation, creep, shrinkage, is sitting on the foundation, different loading, because they are in the long length. You have a different, significantly different geology. soil profile across the bridge length. So you can expect differential settlement, support movement. If bridges are sitting on the bearing, because of the dead load and thing, the bridge movement, there is a friction force. Those things belongs to permanent category. The transient load, the load is going, it's come and go, come and go. It's not station. The main one, we are designing the bridge for traffic. Of course, we talk about collision, impact, the surcharge because of the traffic in behind the abutment, earthquake, wind, water flow, the fire. We talk about this one later. These are transient load. These loads are is in the bridge, but every second is vary within the bridge, especially traffic. Then the thermal effect, because thermal effect we need to consider, because especially in Sri Lanka may not be a big problem, but most part of the world, you got a seasonal changes, the temperature fluctuation is significantly large. Because of this seasonal changes, the bridge temperature, because the bridge sometimes you, for example, this Super T bridge, we build with the closed cell, inside temperature and outside temperature over the years have a significant change, and the bridge average temperature within the bridge because of this change will have a change. And because of that, there is a significant average bridge temperature variation within the bridge length and the cross section. So you need to design for them. So these are the three main elements we design a bridge. But in addition to that, we talk about this one last two sessions, the construction loading. That you can't predict. You don't know how to going to build, how much you're going to consider when you are designing this bridge, but you need to pay the attention. Right? If you are designing a balance cantilever, segmental box girder bridge, a different type of bridge, you need to pay attention, or else you need to make sure that your contract documents cover this part. The contractor need to check during construction. So we get the bridge design, we categorize into three load type: permanent, transient, and thermal. Thermal effect is always there. So next, you need to know how you're going to design the bridge, how you're going to combine them together. To do that one, what I'm going to do, I'm going to separate this load into different categories. The one is the permanent load. It's always there in the bridge. The category B is the traffic load. This is a rail bridge, rail and traffic load. We design the bridge for traffic, then A and B always work together. Sometime in the bridges, we have a pedestrian. We design the bridges with pedestrian access. Okay, maintenance traffic, that is there. And we design the bridge with minimum restraint. Of course, we have to design. We saw that bridge, sometime if it is hit by the flood, not allowed to move. Sometime they overheight the vehicle, sometime push the bridge up. We have to design them to minimum restraint to make sure that at least they have this restraint in the bridge. We discuss about collision, because we don't have the collision all the time. Every time there's the car is passing underneath, it's not going to go and hit the bridge barrier. These are happening, but once in a while, we consider these loads as a ultimate limit state load. We categorize collision load, but we need to design for that load. Then the bridge traffic barrier, of course, we have on the top. There is always possibility that the vehicle go and impact on your bridge barrier on the top. So we had to design for traffic barrier. That is also ultimate limit state event. And then the earth pressure, of course, when there's the bridge, behind the abutment, we got a backfill. So your abutment structure, always when the truck is moving, there is a surcharge due to the weight of the truck. So there is the earth pressure in that one. Of course, you have to design your bridge for earthquake. We consider that one. Then what you need to understand, especially this one, I want to emphasize, especially the road authorities need to make a decision when you are using a different code, how are you going to combine? For example, a permanent effect is there, traffic is there. This is the purpose of designing this bridge. How are you going to combine these two, A and B with H? I will give you one classic example. You are designing a bridge in a local road or in a village area, right? You are designing a bridge in your one of your major highway. That one is quite critical for commercial and other purposes. Let's say the bridge is linking the port, right? You want to, your logistic, so you need to make sure that that link should be functioning all the time. So then you can design for a load combination with the traffic and with the earthquake. But when we were designing bridge for ultimate limit state, we consider the permanent effect ultimate limit state form. For example, if you got a dead load in a British standard is multiplied from 1.35, if I could remember, and then the Australian standard is one. Now I'm confused. This one is 1.3 dead load and 1.8 traffic load. We get this ultimate limit. Bear with me with these numbers. These two combination, but you don't want to combine ultimate limit state combination with the dead load and traffic with your earthquake, because that is also ultimate limit state event. We design the return period is very less. So therefore, you can consider different load combination. The permanent effect plus the permanent effect is always there. The serviceability limit stage condition in your bridge due to traffic with the earthquake, you can consider that one in your bridge design. You can make that decision according to the purpose of the bridge. If you design in this bridge on a low traffic environment area, is logistically is not that important. Sometimes you can make a decision. No, you don't want to do that combination. We just design only for the earthquake. The earthquake effect combined with the permanent effect. That is the reason I just categorize this loading A, B, C, D, E, F, G, H. I is the water flow. It's a similar situation. We are designing the bridge for the 1 in 2000 year flood for ultimate limit state. So it's sometimes it may happen once in a while, one time during the lifespan of the bridge. So then if there is a 1 in 2000 year flood, you know that you don't have any traffic on the bridge. It's no point you combine A, B, and I together, right? Because there is no traffic on the bridge in that flood situation, because the whole access road are under flood, right? But you need to remember this one. After flood is, everything is finished, your cover in the pier, it is there. That is the aftermath of the flood. So you got a 1 in 2000 years cover, but you don't have a flood load. That's cover means you have an unsupported length of your pile that make a massive flexibility in your bridge, whether it can take the breaking load. Then are you going to combine A and B and I together, considering cover depth in your bridge? That is the reason in my previous slide, I show you in the flood data, you need 1 in 100 year and 1 in 2000 year cover depth. So sometimes you can design your bridge for the traffic and traffic load with the permanent effect and the traffic load together with 1 in 100 year flood. The reason is your bridge is above the flood level, it is serviceable. But the way you need to combine them together, you need to think how important that particular bridge structure you're going to use it. And the bridge need to be designed for wind. The wind design is in general is not critical for bridge, but if you design like a cable stay, suspension kind of a bridge, yeah, the J is the governing criteria. Of course, the thermal effect play a significant role in the bridge design, especially in the SLS design, and the bridge behavior play a significant role. The thermal effect is always play with the bridge we design for the permanent effect, and the traffic is always combined together. This is the way I am going to teach you how to design a bridge. Because I'm going to discuss with you, not teach, I'm sorry. I'm going to discuss with you how we're going to design a bridge. So you saw the bridge, the loading, the earthquake, collision, the water flow, wind, thermal, even traffic barrier, all these things, traffic load, most of the thing in this bridge is uncertain. We don't know exactly how much, how to quantify them. Yeah, how to quantify them. Only thing we can do a bit of a quantification in a correct way is the permanent effect. Because of that, the bridge design, you have to be really mindful when you were using the load, when you are combining them. The reason I asked you to do, if you use the permutation and the load combination, plus minus, all sort of thing, you can develop about few thousand load cases. And I'm going to give you an exercise to do, because the next week we're not going to give you the break and give you an assignment to do. I'm going to do an exercise. You can produce the few hundred time load cases. And in addition to that, in that exercise, you will see every section of the bridge, you can create few hundred load cases by yourself. Yeah. And if you combine together in the bridge design, every section, the bridge will be subjected to few thousand load cases. But don't get panicked when you are designing a bridge. With the experience, if you draw a sketch, if you use your structural analysis knowledge, you can identify only very few load cases that govern the bridge. The way we design the bridge, we designed the bridge for traffic flow. Please remember that. We designed the bridge for traffic, to support the traffic. We designed the bridge for traffic, then we check for all other conditions. For example, collision, earthquake, the water, the flood loading, the wind loading, all those things we checked. We checked and we take the necessary action. Please note that, don't mix it up. What the people do, they get few hundred load cases, run this one. I got a maximum bending moment diagram here, minimum bending moment diagram, design, reinforcement, put it in there. Then someone is asked, okay, you go and try to present to, for example, to your client, this is my bridge design. The client is asking, okay, I don't know anything about the bridge design, because I'm a project manager, but just for my understanding, I want you to explain me which load case, because I'm a civil engineer as well, which load case govern this design. Then your answer is going to be, yeah, don't worry, mate. I did my analysis using MIDAS. I got this bending moment diagram up here, down there. It's in the middle here, because my actual bending moment is much less than like this. You can show this diagram. Okay, you can see this is the capacity, this is the load. So fine, don't worry about the load case, right? So that is not a structural engineer answer. When you finish your bridge design, you should know which load case actually, which form of load case, where you put your truck to produce the governing load case. For example, if you design your pile or column, which load case govern? Is it sometimes is governed by the collision? Sometimes it's governed by the earthquake. Sometimes it's governed by the water flow, because some bridges, height is as this picture here, the height is 50 meters. The total height of the bridge is 120 meters. These loads may govern that one, even the wind. You should be able to tell. You should be, when you finish your bridge design, you should have to have that appreciation. So when you explain to your junior engineers, you should tell them there are so many permutations you can work around when you design a bridge, but mate, this is what you need to go to drawing board. This is what you need to look at. We are designing a bridge for traffic, design for that one. Don't forget to check for these load cases and tick the boxes. And of course, there is a situation like sometimes your collision load is governed in the whole bridge. Let's say you designing a bridge 600 meters, but you have a road in only between between two piers, pier number 10 and 11. Then these two governed by the collision design. It's not the pier number 5. But pier number 5 may be in a river, then it may be governed by the flood design. But the flood design in the sense after flood, the scour of the pier will affect the bridge behavior. These are the things you need to keep this one in mind when you are designing a bridge. This is the traffic load, and then I have put this one because this is something related to your assignment you're going to work through. When you put a traffic load in the bridge, I will explain it to you later because I took a lot of time now. The traffic load is a moving load, is a dynamic moving load, is a dynamic load. When you are designing the traffic, you can do 100 PhDs, but still you can't come up with the conclusion. The bridge and the vehicle and the bridge interaction behavior, you can't conclude that one, because if you come up with a solution for one single span, it's going to be totally different for the next span, because when you build the bridge, creep, shrinkage, all this behavior, your bridge deck will be different. Because of that, a lot of uncertainties to get the right numerical model or the answers. Because of that, the code always have a simplification, approximation, how to do it. The traffic is a moving load, but when we're designing a bridge, we use that one as a static load. This flow chart show how we're going to get there. The dynamic load, the bridge and the bridge deck and the vehicle interaction, with a lot of experiment and testing, they use this interaction. When the vehicle moving along the bridge, the static effect, how we're going to convert to a dynamic effect. We are going to multiply by a dynamic magnification factor. This factor calculation for rail bridges and the road bridges, they are very different, and different design code have a different approach. Therefore, you need to you have to use the numbers as specified in your design code, and with that dynamic magnification factor, your dynamic moving traffic load, you convert into a static load. So when you got a static load in your when you convert that one to equivalent static load, that is static load, you get the bridge, the vehicles, you got the reaction transfer from the truck to the bridge deck through an axle to the wheel. Those axle loads, these axle load, as I mentioned in this picture in here. So you develop the bridge live load model. Those live load model, different design standard. We have a different live load model. Then they have a different axle loading models. And the bridges always, when the vehicle is moving, they brake, accelerate, decelerate. So braking and traction is one thing we need to consider in the bridge design. The braking force is a horizontal load on the bridge deck. In addition to that, the bridge is not always in a straight line. You can see the picture behind you in that presentation. In my background is in a significant sharp curve. So when any object is moving on a curve, there is a centrifugal force you need to consider. This is other common sense we use in that one. So this moving load, we convert back to the static load. In the bridge design, we convert this thing into 3 separate load, and this one well defined in the design standard, and we'll tell you where to position them as well. In addition to that, we spend some time today to discuss about the fatigue loading. I think you can see the fatigue effect you need to investigate separately, especially if you are designing a steel bridge. This fatigue effect is a significant part of your design, same as you design the member sizes. But if it is a concrete member, you can check that one. So this is just how we're going to convert the moving traffic load in the bridge design. This is the model we're going to use, and in our next sessions we're going to use them significantly. Any question up in this area?
May I ask a question with respect to this temperature, say the cold temperatures, generally steel is very brittle after minus, I think after 4 degrees. Is there a particular modification that you all use for the strength for steel?
This is again is not on top of my head, Shiromal. What I will do, I will just go back and I will send it to some design information. Yeah, it's a good question you asked, because they, especially like in Australia, like some parties go to, during winter is, but if we talk about like in Canada, like Manitoba, it's always -40 during winter, but they use when they design the steel, the steel bridges, we had to detail and design. I will check this one and I will get back to you.
Thank you.
Any more questions? If not, during weekend, I will send it to you to covering part 1, part 2, part 3, session 1, 2, 3. This is the bridge design part 1. I went through from the people involved in QA QC process to where when we come to design a bridge, what sort of environment you're going to face, what sort of loading you need to consider, how you should consider them to get a clear picture, you to have a clear mind, to develop a clear sense. So this is the this first 3 session. Combining this one, I will develop few questions and I will send it to you, and then please run through them, because it's very important. Then only you can understand, you can grasp everything we discuss in these sessions, because the next session is more or less what we try to do. What we discussed so far, we try to streamline, and we try to learn how we're going to apply those information into a real bridge. How we're going to make a real bridge into a computer screen, to a computer model, and that screen, what we call always the structural engineers play with, the bending moment, shear force, and the torsion. How we're going to deal these 3 forces, how we're going to design out using our concrete, steel, and pre-stress strands. This is a very simple. These are 6 elements. How we're going to do to work around, but it's very complex. Like I mentioned to you in this one, if we just someone go and do the permutation thing, saying you can develop hundreds of thousands of load cases. You can get that much of output in your analysis. You can run your program. In addition to that, when you do your next the assignment I'm going to give you, one assignment is to draw an influence line diagram and to place the truck in that bridge, to develop in couple of sections the actual behavior of your force behavior of your every section when the truck is moving along the bridge. That's we going to use the influence line, because when you design normal structures, for example, you get a beam, simply supported beam, UDL, the maximum bending is WL squared by 8. But when you use the same beam, but if you send a truck along that one, a moving load along that one, you can see your WL squared by 8 is vary. It's got a variation. It's represent that point, represent another curve. That's what we learn. To understand this, we learn in our in the university. We learn how influence line diagram, influence surfaces, and things. So, if you do not have questions, this is.
May I ask another question? One is the building, the infrastructure. There are services like electrical, mechanical services running with the road, the water, electricity. Likewise, how do you all? Is there a how do you all basically design this the structure to accommodate these services?
Yeah, of course. When we were designing the bridges, like the question I asked about the barrier design related question, I explained the bridge movement like a 75, 130, 120 millimeter. So when we have a drainage pipe in the bridge, we have the expansion connections to accommodate that one, or else we make sure that it's not continuous all the way across the expansion joint. And we design with the flexibility and the expansion joint to accommodate those movements. Yeah, we detail them. Yeah, bridge pier, even the electrical conduit running, we have the conduit we embedded with the expansion and contraction joint. We included that one.
Thank you.
Yeah, so the next week we're going to have our session on the week after. That means it's on 29th. Yeah, then 29th I'm going to continue with the bridge design, and in between the next week try to look at the try to answer the questions I'm going to ask, because that's repress the whole 3 session together. Then you will have a good understanding about what is happening around the bridge before we go and start designing them. Next week I'm going to spend some time with the bridge load and its application. They mentioned that table in here, how we're going to play this one around. This is what we're going to discuss in the next week. So thank you very much. So everyone popping in and listen to me. And then if you have any questions, please free to email me. I noticed there are some simple spelling mistakes and things. Please bear with me. And if you notice that one, please rectify yourself and let me know. And if you have any question, please don't hesitate to write to me, rohita.indiruvage@gmail.com. I prefer to send it to my Gmail address, because the office one, if I get too many, it's not easy. And yeah, so now I will respond to you as soon as possible. So then thank you very much, Dilin and Chatumi and CSEC, Shromal, for organizing this one. So then hope to see you guys on 29th. Thank you very much.
Thank you very much. Thank you very much for the wonderful
Thank you, Rohit.
presentation.
That's very
Thank you.
Thank you.
Okay. Good night.